Good morning, everyone, again. So it's a pleasure for me to present Professor Shubin Liu from the University of North Carolina at Chapel Hill with the talk Information-theoretic approach in density functional theory and its applications to chemical problems. Please, Professor Shubin, thank you for being here, and the microphone is yours.
Okay. Hear me okay, right? It's a bit short. Again.
Yes, we can hear you very fine. Thank you.
Great. Thank you so much for the organizers inviting me to give this talk. Also, congratulations to the university for the big event, our anniversary, 50 years. So my name is Shubin Liu. Everybody, good morning or afternoon or the evening, I don't know. Anyhow, so I'm going to switch gears a little bit. So I'm talking about chemistry. So the title is, again, as information theory applied to DFT, and then we're doing some chemical problems. So I'm going to briefly introduce the framework. So we're talking about 2 identities, 3 principles, and 4 representations of this information theory in chemistry. And then I apply this framework to deal with some chemical problems like electrophilicity, its capability of atoms in molecules to accept electrons, and the nucleophilicity is donating electrons, and the regional selectivity is where the chemical reaction takes place in a particular atom, and then steric effect and stereoselectivity. Then finally, so I'm going to talk about some recent development from within my collaborators. So this is the main reference. Talking about this first two part. First two part was summarized in this mini review article. So what is the information theoretic approach? RTA we call it. So actually, it is just simply just applications of information theory applied to DFT. So we're assuming electron density rho here is a probability function. Although rho we know it's not normalized to 1, instead it's normalized to number of electrons n. But still, in chemistry, we consider this electron density as a probability distribution function. So that's the basis. That's the basic assumption. So the purpose we use this is really establish a reactivity theory in density language. Using density, we don't use orbitals, purely density related. So this is a brief summary of this histories. I think the first paper was published many years ago by Paul and his co-workers. So applying this density to apply the information theory to DFT. And then Gauss backwards Paul published in another nice work on it's called Entropy. So they introduced Gauss backwards Paul entropy. And then Roskin Paul in 2000. So using this information or Kullback liberal or divergence, or we also call information gain, to derive Hirschfeld charge theoretically. And then in 2007, we proposed using Fisher information as a measure of the steric effect. And then a few years later, so we're using this information gain or Kullback liberal divergence as a measurement of the electrophilicity and the nucleophilicity at the same time. So summarize using this slide, I summarize all the formulas in information theory. So with Shannon entropy. So S. So this is rho is density, right? Here is only the local function of the electron density. So this is the Shannon entropy density, and then you have Fisher information. So this is the regular one, and then we also found an alternative one. So in that paper, well, no, I didn't list here. So basically, these 2 quantities should be the same, give the same integral value, but the local behavior is very different because this one involves a gradient of density, but here this thing is the Laplacian. So the local behavior is very different, but the total value of the integration is the same. And then I mentioned that this goes backwards Paul entropy. It's another So using the kinetic energy density and also the Thomas Fermi kinetic energy density. So this is coming from this transcribe the DFT into some dynamic description. So to get this entropy. And then this is the regular entropy people used in the literature. So then you have this density or in different format. Okay. So we have some mini reviews a few years ago. So to visualize this this RTA quantities, we're using benzene as an example. So this is sun entropy. So I applied benzene. This is 3D implementation. This is mapped down to a 2-dimension. So this is like this. And then this is first this is conventional fission information. This is the gradient. So you see a huge spark near the nuclear, but then there's a this is basically this is the reason why we use this fission information as a measure of the steric effect. Steric has to do with the nuclear, with the volume, right? The space occupied by atoms in the molecule. And this is another fission information we call alternative fission information. So you can see, even though the total value is the same, but the local behavior is very different. But still, you see spikes near the nuclear. So this is the that's the absolute value. Then there's the next version. It's called relative fission, relative quantities. In this case, you use a reference density rho 0. So this rho 0 could be the summation of atomic densities for molecule, or some other approximations, or some other representations. So again, this is the rho 0. So this one is called relative Shiner entropy, or also called information gain in my case, or people normally in physics call Kullback liberal divergence. Okay, and then you have this is what I introduced by Angeles, who's in the audience. So fission information is called relative fission information. So in this case, you have because you're using gradient, or for the other one, well, alternative, so you use a Laplacian. So in both this case, we use a reference density, right? And this is the regular Renyi entropy, relative Renyi entropy. So again, you use a reference density. So this is first introduced a few years ago by Andres, and also we did some work a few years back. This also. So because we use density as the distribution function, so this probability function is different from the general probability function in the information theory, because in DFT we know density determines everything, right? So when you have different formulas to represent information, then these quantities could be related. Because that's what we found. And they proved, the first one is 2007, we found that the Shiner entropy density is really related to the two forms of fission information. This is the regular one, and this is the alternative one. So this N is the just integration of the electron density. So this is, we proved this is exact. And we found this numerically also is exact. Okay, this is called identity. So this is for Shiner entropy and the fission information. So the reason why, normally this Shiner entropy and fission information are supposed to be independent, right? But in DFT, actually, this is not the case. And then just a few years ago, and then we found another one. This one is for the relative in RTA quantities. For the information gain or Kullback liberal divergence, and then relate to this this is information, relative fission information defined here. So this one and this one. So this is the local. This is the density, right? The fission relative fission information density, and this other one. So they are related by this formula. So this G function is defined through this Laplacian. Again, this rho 0 is the reference density. So again, this is the identity. So again, the reason why it's because in DFT density determines everything. So when you define different ITA quantities, these quantities are not independent. they are somehow independent through these relationships. And then we have a few representations of this information theory quantities. The first one we'll mention is the one I just showed before in the last few slides. The next one we use this function we call shape function. Okay, shape function is really the density of electron density 1 by n, the sigma. So it's normalized to 1, not in total number of electrons. So this will make the this ITA quantities more relevant to information theory, because in information theory, this probability function is supposed to be normalized to 1, right? So this really satisfies that condition. The other one is so the other one is the using this atoms in molecules representation. So in this case, this rho A is the atomic number of electrons for this atom A. So yeah, you need summation all the atoms in the molecule. So it gives you this called atom in molecules representation. So this is shape function that representation. This is the atom in molecules representation. Then recently we proposed another one. So given any quantity here, like entropy efficient information, we'll consider the cases when you gain 1 electron, or you lose or donate 1 electron, and you see the consequences of what this function was, what this entropy efficient information behave. Okay, so this is now we call another representation. Basically, we consider the impact of different number of electrons in on the property, on the behavior. And then the relationship among these representations is pretty actually for this first two. If we use density or shape function, you get the exact very simple, I would say, relationship, right? Whereas this is an entropy in a shape function, and this is an entropy in density the electron density, you get this simple relationship. For if you consider the electron change, so it's like this is the Foucault function, and then some entropy efficient information, or GBP goes back with power entropy, then you can see this. You can use these quantities to predict the reactivity, because Foucault function we know is a really an indicator, right? This is the this electrophilic interaction, electrophilic reactivity. So if you can derive actually using the derivatives, right, to see this. So this last representation is really closely related to Foucault function, in the explicit formulas. And then 3 principles in the ITA. The first one was introduced by Andrews, who again is in the audience a few years ago. So in this case, she proposed the principle of extreme physical information. So basically, start from the physical information. You suppose you impose a few conditions. Okay, 3 or 4, because this is like this density is supposed to be normalized to n, and then the electron is supposed to be satisfy the Pauli exclusion principle, right? This is the conditions. You dump all these conditions together, you get this equation. This is really like a orbital-free DFT, right? This is kinetic energy, you have Pauli energy, and the concurrent, etc. So this is the so this is what I proposed. So basically, in information theory, we can reproduce the orbital-free DFT equation. This is Euler equation in orbital-free DFT. The second principle was introduced by Nadrowski and Paul in 2000. They call it minimal information gain principle. So in this case, you start with the third representation, atoms in molecules, representation of the information gain, or Kubrick-Libler divergence. So this is the way you use the reference. And then if you minimize this guy, subject to the condition that this normalization of this density must be equal to n, then you get this. So this is really just a Hirschfeld charge partition, Hurstwurst partition of the electron density. So because electron density or atomic charges are really ambiguous, right? Ambiguous when we define this, but this is really exception because using DFT, using the ITA principles, you can really derive a partial charge using this minimization principle. The last one is the we call information conservation principle, proposed a few years ago or 10 years now. So again, we start from here, and then we introduce a variable because these two densities, reference density and this atomic density, is really similar, right? And then we do a Taylor expansion up to the first order. We found this guy could be represented by this density difference, which is nothing but this charge we call Hurstwurst charge. Since assuming this atom, this molecule is neutralized, so this summation of all these Hurstwurst charges must be 0. So in this case, you up to the first order, we found that the information is really conserved. Okay, so this is what we did with this information conservation principle in this paper. So we start from this one. This is the definition of the information gain, and then we know this atomic density is a Hurstwurst partition, right? And then we introduce a variable x, which is the difference between the two densities, with divided by this rho a, and then you become this, and then you do a first order approximation, you get this. Okay. So then we compare for this molecule the two cases, right? Information gain and also this summation of these charges. You really want to find difference. So this means the first order approximation is supposed to be pretty good enough in most cases. So also now then we propose to use this guy to represent the capability of atoms and molecules to accept and donate electrons, because when atoms form molecules, the information is conserved. So this means if your atoms is electrophilic, after you form an atom, it's supposed to be electrophilic as well, the same as nucleophilic. So in that case, we can use the information gain or Hurstwurst charge as a representation of this electrophilicity and the nucleophilicity at the same time, simultaneously. So we don't need two formulas to quantify electrophilicity and the nucleophilicity. So we tested this idea in a couple papers. So this is a new, latest one. This is the original one. So we tested a few atom molecules for this system. This is the electrophilic systems because this is carbon cation. So this center is where the electrons will be accepted for this carbon. And for this system, there is an experimental electrophilicity scale. And then we compare these two cases. One is the information gain. The other one is the first order of this guy, which is the Hurstwurst charge, right? And then we found for this systems, about 20 systems, the correlation is pretty strong. It's very strong, actually. But the slope is different because in this formula, you're going to see there's an electric charge here. So this means their slopes are supposed to be just opposite. Okay, so the one is negative, the other positive. So this is for the electrophilic systems where you accept electrons. And then we test the other system with the nucleophilic systems. So these are systems where donate electrons in the chemical reaction. So in this case, again, we have about 20 systems, and then this star marks the place where this chemical nucleophilic reaction will take place. This is the electron donor center. So we know in this case, this is the electron accepting center, right? Again, there is the experimental scale in the literature. So we use this and compare with the two measures. One is the information gain. The other one is the first order of this information gain, which is the Hurstwurst charge. And then we found the correlation is also pretty strong. So these two results. So one is the electrophilicity, and the other is the nucleophilicity. with the same formula, we can find very strong correlations. And then we apply this assistance to a reaction type we call idiophytic aromatic substitution. This is in organic chemistry. This is a very typical reaction. So in this case, so for the benzene ring here, if your benzene has a substitution R group here, so if you do a idiophytic substitution, really depends on the nature of R. Okay, so sometimes it could happen on this also or parasite, but in other cases it would be only happen in the meta cases. So we call this directing also para or meta directing groups. So in the textbooks, there are a few mechanisms. Well, it's very complicated. Okay, but I don't think at least I'm not convinced. So I've been this been puzzling me for a long time. So for example, in this case, for some groups like this, so this is the also meta, also para. But for groups like this, NO2, so this is a meta. So if we put an NO2 here, so your substitution will take place only on this side, not here. Okay. So this in textbooks, organic chemistry talks about lots of explanations, but I'm not convinced until we try this out. So we tried a few groups with the also parasite group put it here, and then we found this. I only used this Hertzberg chart. Of course, you can also use the information again. You get a similar result. So you found the difference is pretty small, but the trend is obvious. So for this group, the Hertzberg chart, we know it's always a small number, but this small number really tells you the difference. So for the meso para groups, it's always these two groups has the maximum number of charges. Okay, Hertzberg chart is the biggest in magnitude. But for the other systems, it is the meta place that's the biggest number. Okay, so this really confirms this information again. Hertzberg chart could be used to predict the regional selectivity, because you have three partitions, right? Which one it goes? It really depends on the charge, Hertzberg chart. Not the other charges, by the way. There's only Hertzberg chart. And then we applied this idea to predict the regional selectivity for a number of systems. So there's no experimental evidence, but we can predict which place this will take place, this reaction to take place. One particular example is here, the NCS and the SCN. The atom is the same, but the sequence is different, right? When one is N bind to a carbon, the other is sulfur bind to the carbon. You can see for this guy, this is also para group. This position, reaction taking place in this place, but for this one, it is a meta place. So this is the we can use this regional selectivity capability to predict the new chemical reaction. That's the so all these calculations for just you do a optimization and you find the Hertzberg chart, right? In Gaussian, that's pretty straightforward. But how about the transition state, the kinetics? So actually, we did the reaction for this simple systems using this is nuclear, and then we use the catalyst. So we did a bunch of systems. So we found this is really Hertzberg chart and the barrier height, which is the kinetics, right? It's really a strong line related to this reaction. So this means from both thermodynamics and the kinetics. So this new information again could be used as a good measure, reliable measure of the reactivity and the selectivity. So the next topic is the Fisher information we use to quantify the static effect. Well, the static effect is widely used in chemistry, and then normally we believe it's relevant to the atoms, right, occupy space. And then in quantum mechanics, we don't have a unique way. In the wave function theory, people use the Pauli expression principle to do this, but Westkoff claims this to be kinetic energy in this paper. And then in 2007, we produced the exact kinetic energy or 1/8 of the Fisher information quantify the steric effect. Okay, because you can from this Fisher information will show you already. It's really indication of the place of the atoms, right, in the nucleus, in the molecules. The theory or not theory, it's to prove what. It's pretty simple actually. Well, I assume if you assume the total energy of a system comes from 3 different physical chemistry principles: steric effect, electrostatic, and quantum, using simple summation abstraction, subtraction, you get this. So your steric effect is really the A times of the 1/8. This is type of here of the information, Fisher information. Okay, and then using this formula, we can define steric energy, steric potential. You take function derivatives, and then steric force, you take gradient, and the steric charge, you take another gradient, and then the steric effect. So we've done a lot, some work in all the years on this. So I'll show you 2 results actually. One is this the you can plot this for both molecules under the crystals. So this is where the sun. So this is really indication of where your nucleus is located. So it's a representation of the space occupied by nucleus in molecule. The one is the stereoselectivity, where we propose to use the steric force, define this. Use take a absolute value to indicate the direction where this chemical reaction takes place. In this case, for example, so this is carbonyl group. So this nucleophile could attack from this side or this side, but the probability determines the C alpha carbon. If this one, if you have a big group, then you have less chance. If you have a small group, have a big chance. Okay, so with this idea, and then we'll measure the steric force. We found on this side it's much bigger, red spot here. On the other side, much smaller. Okay, so we did another systems, the same thing. So this means that this steric force is really at least a qualitative indicator of your stereoselectivity. This is on C alpha carbon. We also did it on C beta carbon in this case. So a chemical reaction takes place on this part, on this spot, and then this C alpha and this C beta. So experimentally, they found this difference. So if this R is this group, so this side is be here. If it's this side, then the other side, the other side. Okay. So this means the C beta carbon is really plays an important role. So we use this steric force. We do prove that this is the case. We can use we find the difference. Difference, of course, is not that obvious as the last one, but we found this very difference. So if this bigger group, so it's this side. If the other small group, then it's this side. No, this small group is this side, and it's bigger group on the other side. Okay. So this is about stereoselectivity. And then just last year, we really deal with these experimental scale. Steric effect has a experimental scale we call Taft constant or Taft parameter. Okay, so it used this ester hydrolysis, right? So you measure this reaction and then use the reaction constant, right, to quantify this steric effect. So we tried 20 some groups. So we found this steric effect. So that's for an experiment. And this is our steric energy. So they have a strong correlation with both the Barry heights. So if we directly correlate it to the R squared is about 2.9. It's still 0.9 something. Okay, we did. And also we found this steric effect parameter. It's related to the steric potential, steric charge, and then the steric force. So this all related to the steric effect. This means. So this is another plot show you the difference between in the steric force and the steric charge when this group is attacked from different side. So from this side with a big chance, so the steric force is smaller. It's smaller, and this one is the charge. And then for this SN2 reaction, we found this very height for this reaction, and also the steric charge. There's a linear correlation. So for this particular case, R group. So R group is different than the reaction. The reaction is have different barrier heights. This barrier height is related to this steric effect. Or the bigger the group, right, the smaller the reaction rate. So that's what experimentally also confirmed. So this is the case. Okay, I have a minute, 15 minutes. So recent developments. So we apply this. We try to expand the territory of the ITA application in chemistry, the information theory in chemistry. The first one we tried was to do a topology analysis of all these quantities. You know, topology analysis in densities, that's well known. It's been done by Bader, right, in many years ago. So they proposed the four we call critical points. So you have a nuclear critical points in the indication where this nucleus is located, and then you have a bond. So this is where the bond related, and then this is the orange is the ring structure. So if you have the benzene, you have ring structure, the ring critical points, and then you have green the C is a cage. So if you have a molecule in a cage, then you have cage critical points. So that's for the density topology analysis by Bader and his co-workers. And they're using this same idea. So the topology analysis basically you do the Hessian matrix, right? And then do diagonalization. You get these eigenvalues. So eigenvalues positive. You have 3 positive, 3 negative, etc. So that's the definition. Okay. So we can do this same thing with the entropy, Fisher information, and then alternative Fisher information and the information gain. So that's what we did with four RTA quantities. And then the behavior is totally different. Also, it provides a lot more critical points than the density and the gradient and the Laplacian. Okay. So in density, in this paper, we had some comparison, but here we don't. I don't present. But if you're interested in this topology analysis, this is a paper. And then we apply this critical points. This is really critical points for this simple systems. This is Cl2, and then this is this is another one. This is Na. This is the sodium chloride. And then we apply this the entropy versus this quantity. So this is what the NCI analysis done by Weitao and others a few years back. So the point here is that we find different ITA quantities that have totally different behavior. Okay, when we talk about the same different kind, like a bond, right? You have this a single bond, double bond, triple bond, and then somehow they could be applied to used for the identification purpose. And then we apply this topology analysis results like a bond critical points or nuclear critical points to relate to some chemical process like a bond stretching, rotation. This is all stretching. And then other physical properties like acidity, pKa values, electrophilicity, eukaryoticity, as I just mentioned before, and then aromaticity. That's you basically use ring critical points, right? We found this correlation numbers. So this is pretty strongly correlated. Of course, we have a data set of, I don't know how many, 20 to 50 molecules. And then like this, if there are, for example, the alternative Fisher information like this. So using nuclear critical points, it's very strongly correlated. So that's the topology analysis. And then we also introduce another scenario. So in the typical information theory, we use density, all right, a shape function. Now I propose a different one. Use the energy density. So for example, you have a total energy or some energy components or something like exchange correlation. So this is the energy density, right? And then I do some trick. So we divide both sides by total value of E. You get this. So we call this scaled density, energetic density. So this is normalized to 1. Can this be used as a probability function? At least we tried. We don't know before we tried. So this was published 2 years ago. So this is for the kinetic energy density is like this. So this is the electrostatic. It's all positive, right? Well, this is it. And what's it called? This is the radial distribution. Okay, and then when you apply this back to the Charalampos entropy of this kinetic density, you get this. Or so this is the Charalampos entropy of the kinetic energy density. Yeah, you get this. And then when you plot, so this the Charalampos entropy fission emission, we use some energy components. Like this one is Pauli energy. So okay, I use Pauli energy. So Pauli energy is really the difference between kinetic energy and the Moustakidis kinetic energy, right? So we use someone as the probability function and plug it into the Charalampos entropy fission information, this alternative fission information, and this relative fission information. So you get it. So you can see, or again, so you can see these plots are very different. So they represent, well, these two look similar, but the values are different. So this is a red bar. You can this color bar, the absolute value is very different. So this means that their behavior is different. Can this be used to quantify or some physical chemistry properties? We just try. So for example, for the pKa acidity or energy difference, this is stability or reactivity. So you can always see there is a strong line. In this case, we use the entropy for we use Pauli energy as an example in this case, or some other systems. So again, this could be used as a quantitative representation of these physical chemistry properties. The third one is the extra state. So everything we did before is for ground state. Now, but using time-dependent DFT, we can access the first singlet extra state or triplet extra state, right? For example, in this case, if we rotate this carbon-carbon bond, so the PS potential surface is really different. So this is ground state, and this is S1, this is S2, and then we can plot the difference between the ground state and extra state. This is an entropy, fission information, they're all different. So then, and then the reactivity like a Fourier function. So this is the information again when you lose one electron, or this temperature we introduced with the Charalampos a while back. So you can see the ground state and extra state, their behavior is very different. See ground state, extra states. The final application we did was using apply this RTA stuff to machine learning. So combined with this new method we call this really divide and conquer. Basically, we cut it we have big pieces, right? A big system is crystal or molecule. Then we cut into pieces, and each pieces then we calculate the information properties, and then use the deep learning. We use this process to predict both probability of the entire system or the animal. So we apply this to liquid water or crystal or proteins. So we try to read a few systems. So the result is pretty using the deep learning algorithms. They're actually pretty good. So this is what so this process is still ongoing. We're trying to many more stuff with the different algorithms, but and then more properties. Still using the same idea. It's this as the descriptors, right? Or called in machine learning, it's called features. So normally in chemistry, computational chemistry, people use different structure, topological descriptors or features. But here we're using the electronic based on information theory. So the big picture we're trying to put together actually in the last few years is really what we call a density-based reactivity theory. So you can see RTA, information theoretic approach is part of the big picture. So in this paper will summarize these. We have four frameworks RTS1, and then you have orbit-free DFT, you have a conceptual DFT, we don't have time to talk about, and then you have the density associated quantities, like you just directly use Laplacian or density or gradient to do the process. And then just last year we summarized another work, all these applications, the status of this approach. So this is our big picture. This is what we're trying to do. So basically, we have two papers. We put together two papers. One is on particular on conceptual DFT, published 2 years ago, well, a little bit over 2 years ago. So we have many people, including the audience, contribute to this paper. And then just last year, we put another one. So this is really DFT, conceptual DFT, right? This one is the way you expand the territory, the scope, a little bit. So we combine all these theoretical frameworks, conceptual DFT, and DFT, molecular orbital theory, and the valence bond theory. So all put together, trying to answer the same problems, answer the same question from different theory perspective. So that's what we're trying to do in this book. And then we also had a series of efforts on what we call chemical concepts from theory and computation. So the first event happened in 2018. We had the CCTC1, and then we had two special issues. One is on this the Chinese general physics chemistry, and then you have theoretical chemistry accounts. And then we have second symposium on CCTC number 2. It happened 2021, but we did this on virtually because of the COVID. And then just not last year, 2023, in Lyon, France, Christophe, and then we put together another event, so the CCTC number 3. And then the end of this year, we're planning to have a CCTC number 4. So this event will be as part of this bigger conference called PacificChem 2025. Will be happen in Honolulu, Hawaii, in December. So you're welcome to attend. So we're going to have 40 60 people to speak in this event. So finally, I want to thank my advisors, the advisor Wei Tao. So because this effort is a long time effort. So I had a number of good friends, my collaborator, and everything I talk about, all the formulas talk about here are available from this package. Yeah, it's a free package actually. You can download, and have some students somewhere in China. Actually, this and also other places I don't have to work with. So this makes this all happen. So I really appreciate it. And then finally, thank you for your attention. Okay, I don't think we have time for the questions, right? So do I stop sharing, right? Yeah. Okay. Okay. That's a good idea. Thank you. I'll stop sharing. So.
Okay, good morning, everyone again. It's my pleasure to present the last talk of this session to Professor Pablo Barberis from UAM here in Mexico. And his talk is Usefulness of Quantum Entanglement for Enhancing Precision in Frequency Estimation. Please, Professor Barberis, the microphone is yours.
Hi. Hello, it's a pleasure to give this talk in application of information theory in natural science. I thank the organizer for inviting to give this talk. So I'm going to talk about usefulness of quantum entanglement for enhancing precision in frequency estimation. So the goal of the talk is to study what happened with the estimator of the parameter we want to estimate is not identifiable, which is something that usually happens when the parameter we want to estimate is periodic. Okay, so this is the goal, and in the talk I will give a small introduction to the quantum feature information, and then I will state the problem and one possible solution. But the bottom line is that when you have a periodic estimator, a periodic parameter, usually the estimator is periodic, so you cannot satisfy the mathematical conditions for saturate the Kramer-Rao bound. So you don't know how to get the minimal error. So basically that imposes some limits in quantities that diminish the error at sensing time. So I will state the problem precisely and a possible solution. So what does it mean, parameter estimation? So basically, when we estimate a parameter, we never measure the parameter directly. No? For example, if we want to measure the length of a table, we don't measure the length of a table. We measure a mark in a ruler we put on the table. And we assume there is a strong correlation between the mark in the ruler and the length of the table. So basically, each different person that measure that use a ruler to measure the table is going to measure different quantities, no? All around all close to each other, but for different quantities. That can be modeled using a probabilistic model. So basically, the outcome of my measurement is a random variable, which is a random variable S, which its distribution probability depends on the parameter we want to measure. Okay, so basically this is how classically we model the outcome of an experiment condition to the value of the parameter we want to measure. If this parameter change, the outcome changes, and this is how we can estimate different parameters. So in order to estimate the parameters, we take the experimental results in a function which is called estimator that gives a real value, which is our estimation. Okay, so what's the problem? We want to, given the outcome of the experiment, to have the best possible estimation that is allowed by the physical laws. Okay, so first we have to define a cost function. Usually the cost function we use for parameter estimation is the variance, and this problem has been solved in the past century. The question is the following: what's the smallest possible error that I can get from the outcome of the experiments for the parameter I want to estimate. And the answer is given by the Kramer-Rao bound. The Kramer-Rao bound, it's a bound, it's a lower bound to the minimal possible error given by the probabilistic model. So this is the Kramer-Rao bound is given by 1 over something called the Fisher information. As you can see here, the Fisher information, if the Fisher information is larger, the minimal possible error is smaller, and basically depends as how much the result of the outcome of my experiment changes when I change the parameters I want to estimate. This basically that's the intuition. So basically what we want to do is to minimize the cost function over all the possible estimators. But the possible estimators live in the function in the space of functions, which is very large. The advantage of this Kramer-Rao bound is that in order to calculate this bound, you don't need you don't have to make a maximization over the space of all the functions to calculate this. This is very easy to calculate. You only need the probabilistic model. Of course, the question is, okay, the best estimator possible given by the mathematical structure of your probabilistic model is one that saturates this bound. It's impossible to get a better estimation. No? Basically, that's the conclusion. Of course, you can have estimations that are worse. So the question is, exists an estimator that saturates the bound? And the answer is yes, it exists. And I have to, this is the Kramer-Rao bound when I repeat the experiment new times in such a way that that experiments are independent from each other. So as you can see, the more that you do the experiments, the best estimation we have, the larger the Fisher information, the best estimation that we have. When the number of experiments goes to infinity, there is an estimator which is called the maximum of the likelihood that saturates the Kramer-Rao bound. Okay, so this is the likelihood. The likelihood is I make the experiment new times, and then I put the outcomes as parameters in my probabilistic model. I multiply all the different functions, and then this is a function of L. The maximum of this function is my estimator, is my estimation. So this is called the maximum of this estimator is called the maximum likelihood. It's very easy to build, and it saturates the Kramer-Rao bound. Just a problem. This saturates given that certain mathematical conditions are fulfilled, which are that the probabilistic model is identifiable. I will return to this later. Okay, what about the quantum case? In the quantum case, the formulation is a little bit different. Basically, in this case, we want to estimate a parameter of the Hamiltonian, which is an scalar, something that appears in the Hamiltonian. And the scheme is the following. I start with a quantum state at time t equals 0. That quantum state evolves under this Hamiltonian. And after some time, I have a quantum state that depends on the parameter on the Hamiltonian. Okay? Then I measure. I decide what I define some quantum measurement I'm going to do with this state, and then I measure. Once I decide the quantum measurement, the problem is identical to the classical one, no? Because I have some outcomes with a probabilistic distribution that is conditional to the value of the parameter. So once I decide the quantum measurement I want to do, the problem of estimation of a parameter of Hamiltonian reduces to the classical one. But then I can make the following, well, this is exactly what I just said. Then I can have the following question. Imagine I can do whatever quantum measurement is possible physically. What's the best measurement I can do for the parameter of the Hamiltonian that is allowed by nature? Okay, so you can answer that. So you see the problem. I have a parameter in the Hamiltonian. classically, you can always get exactly the parameter, but quantum mechanically, you cannot measure directly the parameter of the Hamiltonian. You measure it through quantum measurements, and the question is, okay, I do 10 experiments with whatever quantum measurement is allowed by nature. I want to know what's the best measurement I can do from that parameter. That is answered by something which is called the quantum Fisher information, which is the following. As once I give the quantum measurement, the problem reduces to the classical one. So basically, I look for a maximization of the Fisher information for all the possible quantum measurements, which are characterized by a positive tip operator value measurement. So if I maximize the quantum information, the Fisher information over all the possible initial states and over all the possible quantum measurements, the answer of that is a lower bound to the error, to the best estimation I can make over the parameter of the Hamiltonian. Okay, so here I finish the introduction. What I want to tell you is that we have a toolbox, okay, to study what are the ultimate limits of measurement estimation. Okay, so now I will focus to Ramsey spectroscopy to estimate a transition frequency between two states. Okay, so I will assume I have a two-level atom or a two-level system, which are coupled by some to some dipolar transition but it doesn't. You only need a two-level system, and you want to estimate the energy of the excited state of the transition frequency between the two states. So I start with a probe in some internal state, which is the ground state. I will call 0, and then I apply a pulse or some interaction that put the system in an equal weight superposition between the two levels. Then I leave the system to evolve. Some sense in time t, this is going to be important, and of course the system change, and what I want to estimate is a frequency, this omega, this frequency that appears here. Then the procedure to calculate omega is I apply another Raman pulse and I measure the internal state. The probability of measuring the ground state is given by this function. So basically, this is my probabilistic model. Is the probability of having some outcomes that depends on the frequency, on the value I want to estimate. Okay, so we can easily apply, build the likelihood function for this, and then find its maximum, and then I will have an estimation. So what's the Kramer-Rao bond for this case? The Kramer-Rao bond is given by 1 over the number of times I do the experiments, the number of probes that I am independent, and the sensing time to the square. So if I want to diminish the error, I have three things I can do. I can repeat experiments, I can increase the number of probes, or I can increase the sensing times, and in that case, the error decreases by time to the square. So if the fastest way to diminish the error is basically increasing the time, as long as your system allows that. No? Okay. So now what happens if I have an entangled state? If I have an entangled state, a GHZ entangled state, which is given by all the atoms in the ground state plus all the atoms in the excited state, I am assuming I have n atoms, the Kramer-Rao bonds gives me that the error diminishes 1 over the number of experiments, 1 over the number of probes to the square, no? The numbers of atoms in the GHZ states, and time to the square. So basically, this is one of the reasons one says that with the entangled state we have a quantum advantage measuring some parameters. No? So the problem is the following: is that the probability of finding the atom in the ground state. Now I will go back to the case, to the product case, not to the entangled state. In that case, the ground state, no, the probability of finding the atom in ground state is a periodic function of omega. Okay, basically what this means that given the experimental outcomes, we have a different set of frequencies of estimations that are consistent with my experimental outcomes. So that in this case, we don't know which one is the correct frequency. That means that we cannot saturate the Kramer-Rao bound. So this is one of the conditions. In order for the estimator maximum likelihood to saturate the Kramer-Rao bound, the probabilistic model has to be identifiable. Okay, that means that there is a unique identification between the experimental outcomes and our parameter, and the parameter we want to estimate. In this case, that doesn't happen. So, well, the question is, first, how can I saturate the Kramer-Rao bound? And the second is, how can I take advantage of the time? Because as you can see, if you increase the time, the periodicity in omega increases. So, I will put now some. This is an example of a likelihood of the Ramsey spectroscopy problem as a function of different times. So I will assume that my parameter is between -1 and 1. Okay. So when we have a small time, no, we have only one maximum in the region. So we can do the experiment. We can assume that the parameter is between these two, and we have only one maximum, and that's it. We know that's the estimation. But if we increase the time, remember, if we increase the time, the error diminishes a lot. Okay, but then what happened? We could have two maximum, or three maximum, or two maximum in the region. We don't know which one is the parameter, so the error is not going to saturate the Kramer-Rao bound, because basically we have two estimations. We don't know which one is, so the error is large. Okay, so in order to solve this problem of identifiability, the usual path is the following. I define an interval where I know the parameter, where the parameter is known to be. Okay, so I take that from some clues about the system I am using. Then I choose, if I want to minimize the Kramer-Rao bound, I choose the larger sensing possible time in which the likelihood is identifiable in that interval. For that case, it's this one. And then I can calculate the Kramer-Rao bound with these limits. Okay? And then what you get is, I will only focus in number of experiments as resources, not in time, in this talk. So if the initial condition is n independent probes, and we make new experiments, the minimal possible error is, given that the parameter is inside this region, okay, a region which is of the size 2 times delta big omega, the minimum error is that one. So basically, if I know more about the interval, the error diminish. It depends 1 over the number of probes and the number of experiments. What happened with GIC states? The problem is that when we do Ramsey spectroscopy with these GIC states, the periodicity of the probabilistic model increases. So the maximum sensing time that is allowed in order for the estimator to be identifiable diminishes. And if it diminishes, the error increases with respect to the other one. So if I put this back in the Kramer-Rao bound, we obtain this result. Here is a table which is easy to see. So if as resources, I use the number of measurements with product states, assuming the maximum sensing time that gives me an identifiable estimator that guarantees that I can saturate the Kramer-Rao bound. If I do that, this is the error with product states, and this is the error with GIC stangled states. It is worse. Okay, so it's like if it's like this is a resource I cannot use. No? I know that the Kramer-Rao bond is smaller for this than for this, but the problem is that now I take into account, okay, but you have to take into account that the estimator has to be identifiable. So if you have a system that allows you to measure very large times, and at least if you do nothing, product states are better than GHC states, which contradicts a little bit the intuition for entangled states. So what we want to solve, what we solve in these problems is, are GHC states worse for estimated frequencies, at least in this kind of problems, and how do I take advantage of time for diminishing the error? Because remember, we have if we increase the sensing time, the error diminishes at 1 over the time to the square, so we want to take advantage of that. So the idea is very simple. So I will just state the idea and show you the result of the simulations, and the details are in a paper. So the idea is the following. I define an interval where I know, where it is known the parameter, the value, it is known the parameter of I know that the parameters is inside that interval, the value, okay? And I restringe my estimator there, and I choose a time, a sensing time, that guarantees that my estimator is identifiable in that region. Then I make a lot of experiments, okay? And then I have an estimation and an error. Using that estimation and error, I define a confidence interval where I know that with a very large probability that the parameters is inside that region. No? If I do it correctly, that region is going to be smaller than the original region. So then what I do now, I assume that the parameter is inside that confidence interval, and then I find a sensing time which is consistent with that interval, which is going to be larger, because the smaller the interval, the larger the sensing time, and I repeat the procedure. The advantage is that when I repeat the procedure, the feature information is larger after each experiment, so the error diminishes faster. I do it again a number of times. I define a new interval, and I repeat the procedure. So basically what I do, I start with this interval, I make some experiments, then I reduce the interval, make some experiments, but now I diminish the error faster because my feature information is faster, because my sensing time is faster, and I repeat and I repeat. If my parameter is always inside the interval, okay, I diminish the error and find the error I want to faster than if I don't do this scheme. So these are the details. The details, basically we defined some unitless times and some unitless frequency, and we decided to prove this idea in such a way that my interval reduces as first 1/2 of the original interval, then 1/3 of the original interval, then 1/4 of the original interval. We did that because with that scheme we got some analytical results that allow us to understand if this method is really better or not than the original. So the analytical estimation of the error, which it's not so long calculation, you have to be patient, is the following. The error has two parts. The first part tells me what happened. This CL is the probability of the parameter to be inside the confidence interval. This is something we decide before doing the experiments, and you can estimate how many experiments you need to make in order to reach some confidence intervals. Given the confidence intervals, you know how many experiments you have to do in order to get the confidence intervals you want. So the first part is the contribution when the parameter is always inside the confidence intervals. This is a number of proof. S1 is the number of initial measurement that has to be large in order for the estimation to be normal, so our estimation of the confidence interval is correct. But the interesting part is that it diminishes as the number of measurement to the square, to the cube. And then this is a contribution for the case when the parameters is outside the confidence interval. It can happen, the probability is very small, but it can happen. In that case, if my parameter is outside the confidence intervals, it doesn't matter how many times I do the experiment. It is not going to improve my estimation because I am looking for the parameter in the region where the value of the parameter is not there. Okay, so the bottom line, if the confidence interval is very close to 1, the confidence level is very close to 1, is that if we use this adapted method, we have that the variance decreases as 1 of the number of measurements to the cube instead of 1 over nu. This is not super Heisenberg. Basically, is that we are hiding in the number of measurements the time resource. No? Because now in this construction, if I increase the number of measurements, I also increase the time, the sensing time. Okay, this is what we have this gain, but it's much more better, no, than the original MAU. This is a theoretical modeling of the error, which doesn't have the approximation of the other ones. So this is the variance multiplied by the number of times I do the experiment. The straight line is the quantum Kramer-Rao bound when I don't make any adaptive measurement for the maximum possible sensing time. So this is our benchmark. Anything above this line is worse than the original case, and in the bottom is better. So for different confidence intervals, you always have a region where our adaptive methods is much more better than doing nothing. Okay. Of course, after a lot of measurements, what dominates is the error given by the estimations that are outside the confidence levels. No? Okay. So then we did a numerical simulation of the measurement process for product state and for GIC states. And again, this is the the case where you don't do when you don't do nothing. So this is the numerical simulation. This dot here, this like continuous line, is the case where the quantum Kramer-Rao bound for a confidence level 1, and these points are the numerical simulation of the Ramsey measurement process. And there are two things here. First is that our error calculation works, and the second is that when you do this for entangled state with different numbers of atoms, we reach over 5, until 5. It doesn't get better than doing only with 1. Okay, and the reason is that when you do Ramsey spectroscopy with GHZ states, the periodicity of the probabilistic model increases, that decreases the sensing time. Okay, so that's it. The conclusion is that using confidence intervals and a time-adaptive strategy, we can improve parameter estimation as a function of the number of measurements using increasing the sensing time. So this allows us to basically go around the problem of the identifiability of the estimator. The other conclusion is for this particular case, entangled GHZ states are not better than product states. And well, this was published in 1 month ago, a little bit less in Physical Review Research, and that's the end. Thank you.
Well, thank you very much, Professor Barberis. Then this is the last of our speakers in this session. So we invite the assistants to write probable questions in the chat at Zoom, and also we can pass these questions to the WhatsApp group. So we have a coffee break, so we'll be back in 20 minutes at 11:25 with Professor Angel Garcia Chung as a chairman. So let's see in a few minutes. Thank you so much, and thanks for these three interesting talks for our speakers. Thank you.
Hello, welcome back to this to this session. Our next speaker is Peter Schürger. He's from the Institut de Chimie Physique from the University Paris-Saclay-France. And the title of the talk is An Information-theoretical Take on Electron-Nuclear Wave Packet Dynamics. Peter, microphone is yours.
Okay, thank you very much for introducing me, and thanks to the organizers for inviting me. So, as already told, I'm going to talk about electron-nuclear wave packet dynamics. That means we're going back to theoretical chemistry. And so the general idea of what I want to do is, so we have the time-dependent Schrödinger equation, and we are going to solve this analytically. And then we get time-dependent density from the wave function, and from this we can do some information-theoretic analysis for the dynamics. So let's first start with a general overview with the theoretical background. So we are working in the framework of the 1-1 representation, where you start basically with the Schrödinger equation, and then you introduce the electronic Hamiltonian, which is the molecular Hamiltonian, but without the kinetic energy. And so now you have a Hamiltonian which you where you fix the nuclear coordinate, which is a capital R, and now you solve for the electronic states. So you have an eigenvalue equation where you have here the eigenstates, the nth eigenstates, and the associated eigenvalue. And this basically then becomes a potential energy surface for the nucleus. So here on the right, we have this concept, a picture I took from the book Introduction to Quantum Mechanics, where you can see here the potential energy surfaces, and we have here the nuclear coordinate, and on this axis the energy. And as you can see, basically different potential energy corresponds to different states inside the molecule. So from there, what we do is we expand the molecular wave function into this adiabatic, so-called adiabatic states. So we get nuclear coefficients and the electronic eigenfunctions, and we sum over this. And if we now plug this into the Schrödinger equation, we get a set of coupled equations where the time dependence of the nuclear coefficients basically is the determinant. And you see these equations are coupled by the kinetic operator, which acts not only on the nuclear coordinate, the nuclear coefficient, but also on the electronic eigenstates. And this is sometimes quite involved to solve, and therefore there are a lot of approximations to this equation and a lot of different angles to approach this. And what is also done?
On the other hand, is, for example, this equation is approximated by dropping the terms where the kinetic operator acts on the electronic eigenfunctions. And also we only consider one electronic state, so that the Born-Oppenheim approximation, in the Born-Oppenheim approximation, the Schrödinger equation looks like this, where we have only the the nuclear coefficients, and here the energy surface of the respective electronic eigenfunction. And the full wave function is then recovered by multiplying the nuclear coefficients to the respective electronic eigenfunction. So this approximation works very well when we are far away from so-called avoided crossings or conical intersections, meaning that places where the energy surfaces come quite close. So for example, heuristically, we could say that when we move in this area on this state, we would have the Born-Oppenheim approximation would be very good. But if we come close to a conical intersection, it starts to break down. So let's look what normally what is done in our group. So we have this Schrödinger equation. We do some numerical simulations where we excite the molecule, for example, by light, or just doing some initial non-equilibrium state. And when we then study the femtosecond, attoseconds dynamics, for example, we did it quite recently for Fulvin. And where we treated a normal mode expansion as the potential of the system, the electronic potential, and this was, in some coupling terms, this is the linear vibronic coupling model of Fulvin. And we consider 2 electronic states and 30 vibrational modes. And we excite this molecule. And then, for example, here, we look at the different population dynamics that come from using different methods to solve this equation approximately. And for example, we applied multi-trajectory Ehrenfest, coupled trajectory, multi-coupled trajectory, mixed quantum classical, or different surface hopping schemes. These are trajectory-based schemes, meaning that we treat the nucleus classically as trajectories. And we then we calculate the electron as quantum as possible. And by this, we hope to get a quite accurate description on how the system moves. So here, the work basically was in comparing all these different methods. And this is quite involved and not trivial, since most often, sometimes the exact solution isn't even known. So the analysis is quite involved. So let's look at a little bit more at the physics, what's happening. So we start with a Gaussian state somewhere. In this Gaussian state, moves on the excited state along the mainly contributing coordinate, which is in this case ring CH2 stretch. So this is vibrating. So we move along the stretch, and we see that we here pass, for example, the conical intersection. We get reflected in the ground state, and then we come back to the conical intersections. And here we have a wave packet splitting, where one part of the wave packet remains on the excited state, and the other part goes down in the ground state. We can see this here in simulation data, for example, for some method we studied. We are here in the excited state. We pass the conical intersection. Here we get reflected. Here appears the splitting. And one part on the excited state moves like this, and the other one you can see here. So as you can see, there is a lot of coupling between the electronic states and the nuclear coordinates. And therefore, what we want to know better, what we want to research is the how the nuclear and the electronic degrees are interacting with each other. And so this are like a correlated movement. So we want to study this closer. And what we also want to know more about is maybe we get some measures out of information theory, which we can use to compare and benchmark all these different methods. So that's the point we are coming from. And this is actually quite a complicated molecule. So we are starting with some really simple models compared to this. But first, let's talk about the information theory. So the methods that we wanted to use is a differential channel entropy, where we have where we study some continuous probability distribution, and we plug this into the differential channel entropy. And here, of course, the densities that we want to have are position space densities that we get from the absolute square of the molecular wave function, or marginal densities, and associated the momentum density, which we get from the Fourier transform of the full molecular wave function. And then, of course, we measure something, and then we want to interpret what is this, what kinds of information is stored in these two densities. But having these entropies, what we then also can do, we can calculate the mutual information when we have, for example, two different variables here called x and y. We can calculate the entropies by calculating the marginal densities and the two-dimensional densities, and calculating then the difference of the sum of the marginal densities minus the two-dimensional entropy. You can see here a Venn diagram interpretation of the mutual information. where the mutual information basically is the uncertainty overlap appearing in the Venn diagram of both. Okay, and what's we have to keep in mind is if the mutual information is equal to 0, this means that we basically are stochastic independent. We have stochastic independent variables, and this means we can write the density as a product state. So the mutual information we want to compare with linear correlation measures because they are quite common, and we want to see is there more potential than traditional analysis. And for this, we calculate the covariance, which is defined as you know probably as the expectation value of the differences of to the mean of both variables. And we also calculate the linear correlation coefficient, which is quite well known in stochastics, which is related to the covariance, and basically normed by the width of both variables. Very shortly to the interpretation of these correlation measures. So if you have a density in this XY space, when this density is diagonally stretched at some angle, and you see that it could resemble a linear function, the more it can be approximated by a linear function, the closer the correlation coefficient comes to 1. If you can not approximate this with a linear correlation, with a linear function, or this linear function is either has slope 0 or is vertical, this means both variables are not correlated, so it's 0. And if the function has a negative slope, so if we could approximate it by a slope that goes like this, the correlation is negative. So the strength of the correlation is its absolute value, and the direction, so if it's correlated or anti-correlated, is given through the sign. So if you now compare this to the mutual information, we see that there may be cases where we have no linear correlation. So here you can't approximate this by a linear function, but you see that both variables are indeed correlated. So the mutual information would be bigger than 0, while the covariance and the correlation would be 0. So this means that the mutual information also contains nonlinear correlations. Okay, so before we go to more complex situations, we're going to look at the harmonic oscillator, which is always quite reasonable. So let's look here at some dynamics. So we have the Schrödinger equation, we have the Hamiltonian, and we have here the potential of the harmonic oscillator. And from this, we can calculate the wave function and, of course, the densities. And here, by Fourier transformation, of course, the density in momentum space. We can solve this equation exactly, which is quite nice. This means we can get analytic expressions for the width in position and momentum space, and we can also calculate the entropies analytically by just using the analytical expression for the densities. Also quite interesting is as a detail on the side, you can look at the sum of both entropies. You will see in a moment why we do that. So first, let's look at the dynamics. So here we have some system where we have we start with a squeezed Gaussian state in the harmonic oscillator that is excited in some form, and of course, how we expect that it starts to oscillate. And if it's a squeezed state, the width of the function does also change with time. So that you can see here. So we have here plotted the width in position space, and you can see it's minimal at some point and increases periodically. Here is basically one period, so it's oscillating with twice the period. If we compare this to the entropy, we see that the entropy behaves basically like the width. With just a logarithm, we can prove this by using the analytic expression, and we see that basically the entropy is determined by the log of the width. The same is, of course, true in momentum space. Interesting is only that it's, of course, shifted by half a phase. in respect to the position space, but also the maxima of the entropy are associated with the maxima of the momentum space width, and the minima with the minima. Therefore, what we can say at this point is the information content that we actually measure in this case is, of course, the localization of the wave function. Now let's look at this detail that I wanted to talk about, namely the sum of both entropies, which we compare to the product of both width in position momentum space. And of course, here we have the Heisenberg uncertainty principle, which means that this product can't never be smaller than 0.5, which is quite well known. And here we have associated the BBM inequality, which is basically that the entropy in position and momentum space, the sum of both never can be lower than this value. And we'll see that this is actually fulfilled at the same time when the Heisenberg uncertainty principle is fulfilled. Note this, in fact, this inequality is even stronger. So there are cases where the Heisenberg uncertainty principle is not fulfilled, but the BBM is. Okay, let's look now at the actual model we want to study. So with keeping everything in mind we just talked about. So we want to study the Shin meteor model, which is a quite nice model to study coupled electron-nuclear dynamics. And there we have two fixed nuclei, and we have one nucleus that can move and one electron that can move. And all particles interact with each other. So if you look here, for example, at the potential, we have here the interaction with the moving nucleus and the fixed nucleus, and which are Coulomb potentials. And then we have soft Coulomb potentials, where the interaction of the electron with the fixed particles and with the moving nucleus is considered. And we can tune these by having these parameters RF and RC. And we can do this to get different situations that we want to consider. For example, here we can couple both the excited and the ground state very weakly, meaning that if we study dynamics like this, the excited state is well separated, and we could, for example, think about using the Born-Oppenheimer approximation. While here we have a strongly coupled case, and here this introduces avoided crossing and makes the excited state accessible for the wave-packet dynamics. So let's look at the actual numbers. So here on the left-hand side, we have the weakly coupled dynamics, and on the right-hand side, we have the strongly coupled dynamics. And you can see that we have here the potential that is well separated, where the ground and the excited state is well separated from each other. And here, the nuclear wave packet starts to oscillate and starts to disperse quite fast. And here is the electron. We see that basically follows the nuclear dynamics. If we now compare this to the strongly coupled situation, there we see that the nucleus basically behaves like a harmonic oscillator, and the electron is bound to one of the fixed nucleus on the side. So now we have like all these densities, and we can calculate the total density by just taking the absolute square of the wave function and use this to calculate the total entropy. We can integrate out the electronic degrees of freedom and use this to have the nuclear density and calculate the nuclear entropy, and do the same for the electron by integrating out the nuclear degrees of freedom to have the electronic entropy. And then we can calculate the initial information by adding the entropy of the electron and the nucleus and subtracting the total entropy. Okay, so if we do this, we can again look at some data. On the left here, we have again the weakly coupled case, and on the right, the strongly coupled case. And let's look first at the weakly coupled case. We see that we have here in green the position expectation value of the nucleus, and at the turning points, so when this at the classical turning points, when the electron at the nucleus is reflected, we see that we actually have minima in the entropy. This means basically when coming to the reflection point, the entropy, the wave packet refocuses, becomes more localized, so the entropy drops. And generally, we see that we increase the entropy, which is basically to the dispersion of the situation. Let's look now at the strongly coupled case. There we see that the total entropy and the nuclear entropy behave actually quite similar and harmonic, while the electronic entropy, which you see in the bottom here, is actually quite constant. So we don't see any dynamics here. So before I forget, let me talk about the mutual information, which I printed here in orange. We see that in a strongly coupled case, actually, the mutual information is basically 0. It's here on the bottom. While the mutual information in the weakly coupled case shows the same minima and maxima as the total entropy, and we see the same increase. So there's something interesting happening here. So in both cases, we can compare the entropies, which are the red lines, with the black lines, which are the width of the wave functions. And we see that the minima and maxima actually coincides with the entropies. So the entropies for all cases behave similar to the width. So now the first question that we look at, considering only the first situation first, the weakly coupled situation, what can we deduce the whole entropy dynamics from the nuclear width of the wave function? For this, to look at this, we do the following. We take in Born-Oppenheimer ansatz, because we are in the situation where the Born-Oppenheimer approximation works very well. And we have, therefore, the nuclear coefficient, which we take as the nuclear Gaussian, also we take it as a wave packet, and the electronic eigenfunction we take also as a Gaussian, which is localized always at the same position at the R of the nucleus. And then we fix the gamma by taking the average at time equal to 0, and we plug in as beta the width which we determine at each time step from the actual nuclear width that is taken in the simulation. So we now have an analytic expression. We can Fourier transform this to get the same in momentum space. And from there on, we basically can calculate all the width, the correlations, and the entropies and mutual information that we want, where we have now an expression where we just have to plug in beta or the width of the wave function. And now we can start to compare this. So let me compare first what we see here. So as said before, this is the weakly coupled case, where we have the position space on the left, and we also do the same for the momentum space on the right. And first, we have the exact data in red. We have the numerical approximation that I just described in green. And additional, in the blue dotted line, I simulate numerically the same dynamics, but I use the Born-Oppenheimer approximation, meaning that I only propagate the wave function on the ground state potential energy. And you can see, first of all, that the Born-Oppenheimer approximation actually works quite well. So we can describe all the entropies. So the red and the blue line always coincide. So the Born-Oppenheimer approximation looks actually quite well. But if we now start to compare the green and the red line, we see, first of all, that we overestimate the nuclear entropy, but we have actually quite similar dynamics. So we have maxima and minima at the same point, which only differ by some shift. We can describe the electron entropy quite well, so this makes actually sense. And for the total entropy, we see that we have the same shift as in the for the nucleus. In the momentum space, we actually encounter the same situation. And only difference is here that we have actually no dynamics for the electron. which is because we basically implied that the electron, with the width of the electron eigenfunction is basically constant. So let's look at the analytic answers, analytical results for the correlation. So here it becomes a little bit more interesting. There we have here, of course, the position space and then the momentum space. And let's first look at the position space. There we see that the red and the blue line always coincide. So the correlations in position space are actually quite well. Also, the green lines, especially for the linear correlation coefficient and the mutual information, agree exceptionally well. And if we now compare these both graphs, we see that we have the same dynamics in the mutual information and the linear correlation coefficient, meaning implying that we mainly have only linear correlations in the mutual information and less higher ones. So in the momentum space, the situation actually looks quite interesting because we see first of all that for the linear correlation, the Born-Oppenheimer approximation does not agree. So there we see that we get that the blue dotted line actually agrees with the green line and not with the red line. So the actual data shows something completely else. What is happening for the covariance and the correlation. And we think this probably since in the Born-Oppenheimer approximation, we have less dispersion. And therefore, we have this higher correlation between the variables. Even more interesting is here the mutual information, where we see that the Born-Oppenheimer approximation shows the same increase of the mutual information. Thus, we have, there should be some very high correlations being relevant, while the analytic prediction says that we actually have no correlations. So there's something interesting happening here. And that's what we now want to look in detail. So first of all, let's look at the dynamics. So we have in position space, the nucleus and the electron. We start with some Gaussian state here. And when the dynamic starts, it starts to move diagonally since the electron follows the nucleus. And while it's doing this for later times, for example, the density gets stretched and gets then reflected at the opposite and starts to show some interesting nodal structure. Okay, now let's compare these dynamics to the mutual information. There we see that we start with the Gaussian state at the beginning, and as the time progresses, the mutual information rises to the first extremum, where we have where we can see that basically forms this linear behavior, and the later we go, the more this linear behavior starts to take place, and we have basically linear correlations between both coefficients, both variables. Let's now compare this to the momentum space. There we see that we only increase the width, the horizontal width, but the horizontal width does not contribute to the correlation, to the linear correlation at any point. That's why we saw that the linear correlation basically was 0. But we see that at the maximums, the maxima, the number of nodes is increasing. So the increase of the mutual information is associated with the number of nodes in the momentum space. And so that's a thesis, and we can prove this, or at least we can show this by employing our test density, where we have basically a Gaussian and some cosine, and we can tune this cosine by some variables a and b, where a increases the number of nodes that we see in the density, and b turns the density, turns the angles of the density, where we have a maximum of b equal to 1, where it's diagonal. And we now look at the mutual information and the linear correlation, the following happens. So if we have, if we increase the number of nodes, but we have vertically aligned nodes, we see that mutual information actually does not change. This is what we see in the position space, where the number of nodes is not relevant. But if we start to rotate the nodes in this variable space, we see that the mutual information actually increases with the number of nodes, while the linear correlation basically stays 0. We only have this contribution for early nodes when, for a small number of nodes, when the wave the scale of the Gaussian is the same as the wavelength, because then we get the basically a linear correlation here. Okay. Now let's look at how we can improve our numerical model, our analytic model, and we do this by formulating the nuclear wave function in terms of excited harmonic states. This means that we introduce a Hermite polynomial here. And if you now look at the density we get from this, we see that we increase the order of the Hermite polynomial, we get more nodes, and actually the width of the wave packet also stretches. So this is exactly the same behavior that we see in the position space, where we have nodes. You can see on the right, the nodes are the yellow, the green line are aligned horizontal, and the general direction is diagonal. But if you now Fourier transform this, you see that while we only have here nuclear degrees of freedom, we now have electronic and nuclear degrees of freedom in the Hermite polynomial. And this results in that the density now tilts into the other direction, and the number of nodes, the alignment of nodes is now diagonal, while the main alignment is of the density is horizontal, which you can see here compared with some screen snapshots from the simulation. So now let's look how this improves the actual data, and we see that the linear correlations here on the bottom basically are not changed by this behavior, while the mutual information in the position space, which are the red crosses, are the new values. Actually improve slightly, improve less, and the mutual information in the momentum space actually shows different dynamics in Feroli terms, because we only estimate the number of nodes, and of course we don't take the asymmetries of the density in account, which are important in the first few femtoseconds. But for later times, we agree actually quite well, and we get this increase of the mutual information momentum space. So let's now shortly talk about the weakly coupled dynamics at the end. So there we have we can also do an analytic ansatz, where we have a Gaussian wave packet and an electronic eigenfunction, but now we take the electronic eigenfunction fixed at some place. And this means that basically the electronic eigenfunction and the nuclear wave packet decouple. And now this is, you can see from here that basically this means that the mutual information has to vanish, because we have here a product of both states. And this is actually what we saw earlier. And if you now calculate the entropies and mutual information as before, only the entropies as before, mutual information we don't have to calculate, we see that we actually get a perfect agreement. So the dynamics here are actually quite easy compared to the Born-Oppenheimer case. But what we can also do, and I want to just speak very shortly about this, is we can decompose the density using the Born-Wurm representation of the wave function, meaning that if we now take the absolute square, we get matrix elements. And these matrix elements, from the diagonal parts from these matrix elements, we can calculate entropies as well, which we call decomposed densities or state-specific entropies. And we can do this here. I did it, for example, for the total entropy, but you can, of course, do this for the electronic entropy and for the nuclear entropy as well. And if you, it's quite interesting that if you now take the sum of these entropies, this total as a sum behaves as an entropy again as well. And now you can compare the sum of these entropies with the conventionally calculated total entropy, which is done here in the bottom, and you see that this actually agrees quite well. So therefore we see that the main contribution is actually from the diagonal parts of the density. And also this reflects something about the kind of the non-adiabatic transitions between the different states, Because if you know, for example, look and compare this to the electronic entropy, where we have spikes at these transitions. Transitions happen because there's like a large population transfer between the different states. And you see, we have here the spikes, and they happen at every transition. While, for example, in other cases, it does not. So here we have a different kind. So like the electron transitions differently between the states than the nucleus does. This means that basically we have no overlap, basically a clean cut between the different states from the perspective of the nucleus, while in the electronic space, we have an overlap between the transitioning densities. In the momentum space, this actually looks much more complicated because it has a much more complicated structure, and there are much more overlaps happening. You can see this, for example, here in the electronic case, where we also have these spikes at the non-adiabatic transitions, but we also have an increase of the entropy between it, while here we basically agree very well for the times that are far away from the crossing times. Okay, with this, I want to actually conclude my talk, and I want to finally thank, of course, my people from the University of Würzburg, and first of all, Dr. Volker Engel, which I did this work with together. And I also want to thank my boss, of course, my boss now in Paris, which is Dr. Federica Agostini, which you can see here. And special thanks, of course, to the organizers for inviting me.
Thank you, Peter, for your talk. Thank you, Peter, for your talk. If you have questions, feel free to write them in the chats, both in WhatsApp and YouTube. And let's introduce the next speaker. Thank you, Peter.
Yeah, thanks a lot.
Our next speaker is Dr. Moyocoyani Molina. He is an independent researcher, and the title of his talk is An Information-theoretic approach to characterizing concurrent processes and transition regions along the IRC, a 15-year retrospective on chemical reactions. Moyocoyani, the microphone is yours. Please go ahead. Okay, so 1 minute to adjust some issues here. Sorry for the delay. Okay, so we're back. Excellent. Let's go. Thank you.
Okay. So what you are looking in the screen is a small but powerful fragment of one of the most insightful papers written by Seasonshine. Basically, the concepts behind this is technical aspects of our concepts, numerical accuracy, over interpretability. And the main idea behind this is, at least 18 years ago, quantum chemistry was leading into a way that we start to give more weight to the technical details than rather to understand what is happening, right? And this was 18 years ago. 18 years later, I don't know if it's still true, but one thing that I know for true. Okay, cool. One thing that I know for sure is that after reading this article is that I understand why Dr. Esquivel, Dr. Rodolfo was pushing us over and over in order to describe the phenomenology of the things in chemical reactions. So because we want to give this weight to the concepts, we want to bridge in the gap between the technical details, the technical aspects, and the concepts of what is going on. And we did this through using the information theory. So this is what we are going to talk about right now. We are going to talk about how we use information theory in order to characterize these different processes in chemical reactions that we call concurrent processes. This is a work that we were doing for 15 years, but also I'm going to try to bridge in the gap and try to explain why these information measures work in the way that they are working. As I mentioned, my name is Moyocoyani Molina. I'm an independent researcher, and these are the topics that we are going to tackle today. The first one is going to be the theoretical background. So, because I know that there are some physicists, some mathematicians, or some chemists in the meeting, I will try to establish some building blocks so we can try to understand how we model chemical reactions. The second topic is going to be the foundations. I'm going to explain how do we use information theory in order to describe these different processes. And in the third topic, I'm going to bridge in the gap. This is going to be some unseen results. Actually, to be honest, when I was creating this presentation, I found these results. So I decided that I can put it in here. Let's start the discussion, and let's see how it goes. And finally, we are going to have the conclusions. So, should we start? Theoretical background. We are going to talk about chemical reactions. So we need to understand what is a chemical reaction. A chemical reaction is a process when new substances are going to be made by breaking unforming bonds. So basically what is happening here is that we are going to have some bonds that are going to be break, that are going to be formed, you are going to have some nuclear arrangements, and in the moment that you break a bond, and sorry for that, this is a typo for me, when you break a bond, you require energy to break that bond. And when you form in the bonds, you are going to release that energy. And this back and forth of the energy can take us to the second concept. Because we can trace this energy, we can go to the potential energy surface. So thanks to Henry, Polanyi, and others, we have this theory that if we have some coordinates that can tell us how the molecules are going to approach to each other, how the configurations are going to change, is that we can calculate the energy. How do we do that? Under the Born-Oppenheimer approximation, what we do is we grab some of these particular configurations, calculate the electronic wave function, and we obtain the energy. We move to the other configuration, calculate the electronic wave function, and then we obtain the energy. So on and so forth. And we are going to have something similar to this. This is the potential energy surface, and we can think this guy as a landscape of chemical reactions. You are going to have some valleys, you are going to have some peaks, but one of the most interesting part of this is this guy over here, a saddle point of the second order. Why is it interesting? Because it takes us to the third thing, to the third concept, that is a transition state. We conceptualize that this saddle point, that is a transition state, can connect two or more minima. So the idea for this in chemical reaction is, if we have the transition state, that is a saddle point, and we found a vibration mode that can connect with any of these minima, then we can start to trace a path that is based on weight weight mass coordinates, in weight Cartesian coordinates, and we can relax the path towards the minimum. That can be the reactants, it can be the products. So if we trace these points,
is that we obtain this thing that we call the intrinsic reaction coordinate. And this is how we, in chemistry, in computational chemistry, we can describe the chemical reactions, right? So maybe you are asking, this conference is about information theory. You are not telling nothing about information theory so far. Yes, this is going to happen after this. So basically, this is how we used to model chemical reactions. But what happened after that is when we can apply information theory. So what we usually do is we grab this intrinsic reaction coordinate, and all of those different points we trying to characterize it, which take us to the second part of this agenda, that is the foundations. Technically, what we are doing is to graph each of these particular points, apply the information theory descriptors, and we demonstrate that we can characterize important processes that are not visible in the energetic profile. How do we do that? We were mentioned in the last talks. Maybe you saw that we're talking about the electron density. So I'm not going to explain a lot of it because we already explained it during the day, right? But basically, it's a distribution of probability, the probability of finding an electron in a particular volume. And one important thing is that we assume that we can define all the properties of the ground state of a molecule by using this guy, the electron density. So if we can use a probability distribution that contains the information of the molecules, is that we can use information theory measures. And what we did for all these different years is, okay, we apply these information measures and we try to characterize what is the meaning of applying this information descriptor into the density. One of the measures that we were applying is the Shannon entropy. One of the things that we found is that Shannon entropy can be related to the compactness or extension of molecular volumes. Some people found that it can be related to aromaticity. And this is an interesting work by Borrales and Martinez when they calculate the derivatives of the Shannon entropy, and they found that they can create some sort of index that can tell you in which particular moment of the reaction a bond is about to break, and you can quantify by using this index. So as you can see, Shannon entropy can be related to all these different concepts. For the disequilibrium, we can think disequilibrium, that this is the definition, or it can be one of the orders of the energy information. You can see that this can be related to structural rearrangements and distortion of the electron density. One particular aspect is, if you take a look at the form of the function, is that you are trying to give more weight to the weights. Why? Because when you expand this to the square, it is going to put a the heights of the peaks of the distribution are going to be outstanding more than the rest of the distribution. So that's the reason that this can be associated with structural arrangement. And also we have Fisher information. Fisher information is one of the most important descriptors in information theory. And to be honest, to associate only with three particular concepts, I think that is not fair for Fisher information. But I only put this because it can give us a chemical sense of what Fisher information can detect in chemical reactions. One, as Shubin Liu mentioned early in the morning, could be the steric effect. Another one you can associate with the kinetic energy. But also, we can say that this is a measure of the disorder of the electron density. Okay? So with these three information measures, there are more. And I'm going to talk about only these three during this talk. With these three information measures, we were able to characterize different aspects of reactions. How? Let me put you a quick example in here. This is what we call the concurrent processes for the abstraction reaction, and we apply the different information theory descriptor to this reaction. As you can see here, you are going to have the intrinsic reaction coordinate, but not in terms of energy, in terms of the different information measures that we apply to the electron density. So for those who know what is the abstraction reaction of the hydrogen, imagine that you have an hydrogen molecule, two hydrogen atoms that are bonding together, and then you have another free radical that can be also another hydrogen atom. At the moment that they approach to the molecule, the bond starts to break between the original molecule, and then a bond is going to form with the radical and one of the other hydrogen atoms. And with this, we are going to have this transition between reactants and products. With the information theory, one of the things that we can do is we can evaluate this for the position space and the momentum space. For the sake of the conversation, I'm going to focus only on the position space. If you see the Shannon entropy, you can see how the Shannon entropy starts to decrease until it reaches a minimum, close to the transition state. By doing some comparisons with several measures like the hardness, like the chemical potential, like molecular electrostatic potential, we relate this minimum of the Shannon entropy with the bond breaking, right? The same exercise we can do with the other measures. With the disequilibrium, what we got is there is a maximum, and we named this as a BCR of bond cleavage energy reservoirs. That is the part when the molecule is about to break the bonds, right? But one particular thing, and this is interesting, is that you can see that the three of them can characterize the transition state. And this is interesting because, and this is the moment when I try to say, okay, I think that I can go further with this presentation. If this is true, and we already saw that the different information descriptors can describe different aspects, it means that if something happened in the transition state that was detected by Shannon entropy, something happens that it was detected by Fisher, and something happens that it was detected by disequilibrium, and perhaps it's not the same phenomena, because each different measure can measure different things. So with that in mind, is that I trying to explain why these information measures works in the way that they work, how they help us to characterize this phenomenological behavior of the different chemical reactions. Because we don't do this only for the abstraction reaction. We do this for the SN2 reactions, like 2 reactions. I remember I do this for 4-fold DL-Salder reaction. We do this for also acetylene insertion reaction, and we're trying to characterize all these different steps. But having in mind that perhaps there are some overlap between the different processes is something that was sticking to my head, and this is what I trying to came to this hypothesis. So the hypothesis is, if the different information measures can detect specific parts or specific properties of the electron density, when you go to step A and to step B, you can say, okay, there is a break, a bond is breaking, and then I move to the step C, and then the nuclear arrangement happens, right? Or it could happen that when you move from step A to step B, the bond break and also the nuclei start to get rearranged. So it can happen that we have simultaneous process in one step. How I can have the sense that this hypothesis can be true? We have the evidence. Information theory descriptors characterize this phenomenology of the chemical reactions. So we already have this fact. The second fact, remember that article of Barrales and Martinez about the index of the Shannon entropy connected to the bond? Well, if we calculate the derivatives not only of the Shannon but also of these 3 measures, we can start to characterize all the different concurrent processes, like the maximum and minimum, but also the maximum and minimum of the first derivative of these 3 measures. So with this, we are going to have more information about what is going on. And we have a conjecture. And this is the conjectures that I already mentioned. Information theory descriptors are going to measure different things, but complementary. Let me try to give you a little glimpse of what this conjecture is going to take us. Actually, one good thing is when Shubin Liu shows us some molecular density, you are going to see that it is going to be some relationships with this conjecture. So what I did is, this is not proven yet. It was only a quick test, and I run it into a Gaussian mixture model, and I put 2 Gaussian distributions that can be bonded together. I change the height of the peaks, the standard deviation, so on and so forth. And what I tried to see is to check in which part of the density distribution, what I try to see is when I convert by using Shannon entropy, disequilibrium, or Fisher information, in which part is completely different compared to the original distribution. And what I found is, for instance, for this Gaussian distribution, the different parts is the regions that are close to the peak, but also if there is an overlap in the distribution, this is the part that is highlighted. So Shannon entropy can highlight these different parts. If you think that this can be electron density, that is not the case. Again, it's a conjecture and it's not fully tested. But if you assume that this is electron density, you can associate Shannon entropy with the bonding region. And it's in agreement with the other things that we already discussed. So makes sense, at least for this moment makes sense. And the disequilibrium is close to the peak of the distribution. So maybe you can associate this with the nuclei. And for the Fisher information, this is interesting because of the shape of the Fisher information about the gradient, what it takes my attention is that for this Gaussian mixture model, the main difference are in the regions that are close to the peaks and the regions that also connect the minimum that is in the overlap, but it's not detecting the overlap. So again, if you try to extrapolate to electron density, that is not electron density, maybe you can assume the Fisher information is it's measuring all these changes that connects the part of the nuclei, that is not the nuclei per se, with a portion of the region that is going to be extended to the connection of the bond, but not the bonding per se. So with that conjecture in mind, and the evidence that I told you before, is that I decided to do this. I pulled all the data that I have from Freyper's calculations, I don't run any chemical calculation because we already have it. I do the numerical detection of the critical points for Shannon, for Fisher, and disequilibrium in position space. And I do two things. I characterize the reaction profile based on this new information, and also trying to find if I have these simultaneous steps across different reactions. So the difficult part was trying to see all that information in one single plot. Perhaps I could show you how these different information measures are compared to the molecular electrostatic potential, calculate to other different descriptors. So what I create is this infographic. I'm going to explain how you can read it. So basically, you are going to have the detected concurrent processes by any of these measures, okay? And you can focus your eye in any point that you want. Let's say this one. If you move to the top, you are going to see the energy values to that particular process. But also you can identify which measure was capturing that process. If you see this pattern that are like diamonds, it means that this is disequilibrium. If you see a pattern that is a wavy pattern, you can say that this is Fisher information, and the diagonals is Shannon entropy. If it was a maximum or minimum, you can tell by the shape of this little icon. So with that information, you can say, okay, these concurrent processes was detected by a minimum in the disequilibrium, and this is the energy value. But also you can see how is the molecule behaves in these different concurrent processes if you take a look at the bottom of the chart. So with this representation, there are two things that I want to emphasize. And also we have the change in the derivatives. So if you see one of these abbreviations, you can say, for instance, it was a change in the derivative of the Shannon entropy that increases the rate. So that's the meaning of these other points. So with this, we can extract three different things. One, as you can see, there are processes that occurs at the same time with different measures. If Fisher information, it's related with this zone, with this region that is between the nuclei and the bonds, you can say, okay, at this particular moment, something happens with this electron density that has a lot of disorder, and at the same moment, the disequilibrium or the nuclei are going to start to diminish this amount of change. But at the same time, if you take a look at the transition state, we have that at a transition state, three things happen at the same time. And this is in agreement with what we say about the SN2 reaction. We say that it's a synchronous reaction when one bond is breaking, the other is forming, and we have this bipyramidal geometry. So you can say that the information measure can capture this. Shannon entropy achieves a maximum. Fischer information a maximum, and disequilibrium a minimum, which means that there are some changes in the bond at the same time that there are some changes in the nuclear arrangement, at the same time there is this distortion in the electron density. It happens at the same time at the transition state. So this is the first thing. And the second thing with this kind of diagram, what you can try is to describe the evolution of the reaction in terms of these concurrent processes. So you can say, I start from the reactants, then I know that the bond is about to break, and the rate of the compactness of the density starts to increase. And you can tell in the second concurrent process, because the distance between one hydrogen and the other carbon atom decrease a lot in that part. So it means that this part of the process is coherent. Then after that, after the molecules starts this process, when they are going to approach to each other really, really fast, is that we start to have, we are going to see a rearrangement in the nuclei, and also we are going to experience some drastic changes in the electron density. Then we are going to start with a minimum de Shannon entropy. So we expect that after this point, we are going to have some changes in the bonds and the breaking and the forming of the bonds, so on and so forth. Because of the time, I'm not going to explain the entire plot, but basically, this can be one of these functionalities. And with this, you can map the entire process. Now, the other thing that I found, and this is regarding to the number of steps, I tried to compare only 3 reactions. I did it for 6, 7 reactions, but I tried to compare only 2. 2 symmetrical reactions that are different, and 1 Diels-Alder reaction. And what I do is, okay, now that I know that the different concurrent processes can tell me different things, I'm going to try to put all of them in the energy and try to see how many steps are before the transition region, how many steps are occurring during the transition region, and how many of them after the transition region. And we can start to see some difference between the mechanics of the different reactions. So one thing is that the SN2 reaction is the process that contains more concurrent processes or steps compared to the rest of the different reactions. But this is the interesting part. If you take a look what happened before the transition zone, the abstraction reaction only requires 3 steps in order to go into the transition zone, and the Diels-Alder only 2. Which means that the SN2 reaction requires a lot of extra processes in order to enter the transition zone, okay? Second thing, after the transition zone, and this is interesting, the Diels-Alder reaction is the reaction that takes more steps, more concurrent processes. And this is in agreement with what we know about the reaction mechanism. The Diels-Alder reaction, when passed through the transition zone, it starts to reaccommodate all the different structures. So it requires more steps after we move through the transition state. And this is different with what happened after the transition state compared to the SN2 reaction and to the hydrogen abstraction reaction. And one important thing is, for the Diels-Alder, as you can see in the transition state, actually this point is only for the energy in Diels-Alder reaction. For the other reactions, we have 3 different processes that take place at the same time. So with the concurrent processes, we can start to see this difference in the mechanics of the reactions. And with that, I can give you my conclusions. So with this idea, I think that we can support one work by Yepes. Yepes start to propose some sort of index of synchronicity, because if you think a little bit, asynchronous and asynchronous reactions, it doesn't mean that it is a Boolean logic, right? You have some sort of asynchronicity of some sort of synchronicity. If you start to count how many of these steps can be simultaneous, maybe you can start to have an idea or an index of synchronicity. Other conclusion is some chemical reactions are going to require more or less steps than the others. And I think that this is chemically intuitive. And this is something that we can detect by capturing all the concurrent processes. Also, we found this unified description of the chemical reactions because we assuming, and this is in connection with the conjecture, we assuming that they are measuring different things. And because they are measuring different things, when you put together, you can have a broad description of what is going on in the chemical reactions. So with that, I want to close this with another portion of the same paper of Shaikh that he was citing Wigner, and it says, it is nice to know that the computer understands the problem, but I would like to understand it too. So with this, perhaps we can also understand what is going on. So thank you so much, and I will happy to answer all your questions when you send it to the WhatsApp or other medium. Thank you.
A lot of thanks. Thank you, Moyocoyani, for this interesting talk. Let me emphasize that we still have the opportunity to ask questions to Moyocoyani, whether in the WhatsApp or in the YouTube channel. And now we will have a break, a coffee break, for about 20 minutes. So we'll be back by we will be back by 12:55 here in Mexico City time zone. Thanks. Hello, welcome back to the second part of this session. Our next speaker is Professor Charalampos Moustakidis. He's from Aristotle University of Thessaloniki. And the title of his presentation is Applications of Information Theory to Compact Objects, Configurational Entropy as a Stability Criterion. Professor Moustakidis, the microphone is yours.
Thanks. First of all, I would like to thank the organizing committee for this honorable invitation to participate in this conference with a related talk. As I told you before, the title of my talk is Application of Information Theory to Compact Object. I will specify the topic in configuration entropy as a stability criterion. The table of contents of my talk is, firstly, I will discuss discuss about the information theory in compact object. Secondly, I will present the definition and application of configuration entropy. I will present the TOV equation, which is the equation of the Einstein equation describe the relativistic compact object like neutron star, quark star, and etc. I will present also some analytical solution of the TOV equations, some application later of configuration entropy to this realistic compact object with the results, some application in general in fermion and boson stars. Finally, I will conclude and I will present our collaboration and the relevant references. Okay, first of all, information theory in compact object. There are many applications of information theory to a lot of physical systems. We know both in quantum systems or Newtonian system, from microcosm to macrocosm, many applications. And the last year, there is a strong interest to study or to apply the information theory to study astrophysical objects, including mainly white dwarf, neutron star, black hole, even quark star, and etc. One of the versions of information theory is the configuration entropy, which is a theory based on the density distribution of this compact object. Of course, this configuration entropy related with many applications, not only in compact object, but also in other, let's say, topic in physics. For example, in particle physics, in cosmology, and etc. Many applications. The first idea about the application of configuration entropy was by Professor Glaser, who wrote a paper about the stability regions of neutron star, but in the framework of this very simple Fermi gas model, and also they apply this theory, the information theory, also in boson stars, and they found that there is a strong correlation between the minimum of the configuration entropy and the point of the stability of this object. This was very important, since if one finds a way to relate the stability with a minimization of configuration entropy, this is another way to study the stability problem of this object. We start to thinking about this, and we write also two papers. In the first paper, in 2003, we try to repeat all these kind of calculations and to see if this is a general rule. We study neutron star, quark star, and hybrid star, and firstly, and we found that this rule is not general. It depends strongly on the equation of state and some assumption about the density distribution, about the structure of this object. Later on, we continue with, we try to generalize this idea and to include also boson and fermion object, and try to find if this this theory, to apply this theory to see if there is a correlation also between the stability of this object and the configuration entropy. I will discuss more details later on, but this is the introduction and summary about the main part of my talk. Okay, some visualization of the compact object. Maybe the most of you know some about this stuff. First, we have the neutron star, which is a star with a very compact object with a mass around for 1.5 to 2 solar masses and radius around 10 kilometers. They are very, very compact with a high density. And they have also very, how can I say, they have a very complex structure inside. For example, in the interior, there is a fluid, mainly consists of neutrons and a small fraction of protons. And outside, there is a solid crust. They have a complex structure. Of course, if we want to study this object, we have to apply general relativity. The second object is the quark star. Up to now, we don't have some observations or evidence about the existence of quark star, but there are very serious theories which support this idea. Quark star consists mainly of free quark matter, up, down, strange quark. Also, they are very compact object with a radius even smaller than the radius of neutron star. And there is an open problem for astrophysics to find this kind of object. And the third one is the hybrid star. Hybrid star combine neutron star and quark star in the meaning that in the interior there is a quark matter because the density in the interior, in the center of this star is very, very high. And outside there is hadronic matter, that means mainly consists of neutrons and, as I told before, a small fraction of protons. In our first paper, we concentrate our study in these three kinds of objects. Okay, let's start with the definition of the configuration entropy. The key quantity of the configuration entropy is the density distribution of this kind of object. The density distribution, which contain information about the structure of this object, and they have, let's say, kind of contain information about the quantum behavior of the particle, proton, neutrons, quark, etc., and also information about related with the general relativity, with the gravity and quantum mechanics. And firstly, we have to calculate the Fourier transform of this density distribution given by the equation 1. And later on, we defined a second function related with the Fourier transform, which is given by equation 2. And finally, we defined this function in order to ensure that this function is always less than 1. And the configuration entropy is a fractional of this quantity given by this expression, which looks like, let's say, Shannon entropy. But this is in momentum space. It looks like Shannon entropy, but in momentum space. Okay. Of course, one has firstly to calculate or to find which is the density distribution inside of this object, to calculate the Fourier transform, and finally to calculate the configuration entropy from equation 3. Now, in order to study this kind of object, we have to solve the Einstein equations which describe the interior of this object. This is a couple of two differential equations given by this expression, 4 and 5. Of course, we need equation of states about the fluid inside of this object. The equation of states is the relation between energy and pressure. And one has to include, this is the input to solve this kind of differential equation in order to calculate the bulk properties of this object. That means the mass, the radius, and also the density distribution. Okay, just to summarize the idea, firstly, the calculation recipe is the following. First, we have to start with equation of states. Of course, for example, in order to describe neutron star, there are many equation of states which describe this object, since we don't know exactly which is the equation of states in the very high density of hadronic matter. That means we have a lot of suggestions about the equation of states. The same for quark star and the same from hybrid star. Okay, now having, for example, an equation of states, one solve the top equation 4 and 5 simultaneously for a specific value in the center of this star, central pressure or central density. And for each configuration, we get the density distribution, the mass and radius of the star, and also we get, finally, having the density distribution, we have also the configuration entropy. Of course, this is related with the density distribution. We have a lot of configuration, the infinite number of configurations in any case. And I plot here how it looks like. Firstly, I'd like to say, I'm sorry, just to show again, these equations, this is describe the equilibrium inside of the star, but they are not ensure the stability. If we solve this equation, we have a configuration which is in hydrodynamic equilibrium, but we are not sure if this is stable or not. For example, here is a picture to show you how it looks like this, how to calculate or how to predict these equations, because we have two forces. The first one is the pressure of the fluid with outside of the star, and also we have the gravity, and there is kind of equilibrium. Now, solving the top equations, what we get? We get this kind of MR diagrams, mass and radius diagrams, as you can see here, for various values of the density, of the central density or central pressure inside of the neutron star. You can see here that all this region is correspond to stable region of neutron star, up to the higher value of the mass. This is the critical point. On the left, on the right, there is a stable configuration in equilibrium. On the right, they are unstable. This is equation of states corresponds to neutron star, and for example, this equation of states in this case, which correspond to quark star. But in any case, we have this kind of configuration, and it's more or less easy to calculate in each case the configuration entropy and to find if the minimum of configuration entropy corresponds or is in agreement with the maximum value of the mass. Now, actually, in order to study the stability of this object, there are three, let's say, traditional methods of stability. The first one is to find the binding energy and to minimize the binding energy given by this expression. This is the same like in the nucleus. When we try to find the binding energy of nucleus, we follow the same procedure. The second one is to use a variational method developed by Sara Sakar, and the third one, which is used in this study, which is called traditional method, is to find where is the maximum, as I told before, where is the maximum mass. When we found the maximum mass for each equation of states, we said that this is the stability point. On the right, all the configurations are stable. On the left, the configurations are unstable. Of course, there is convergence between these three methods. But we think that if we found another way from information point of view to calculate or to find or to predict this stability point, this will be very important. For example, there are many questions. If is there any one-to-one corresponds between the minimum of the configuration entropy and the stability point of each analytic equation of state? Is this rule universal? Is it possible, even in some special cases, to associate stability with minimization of CE? And if so, which is the underlying reason? Obviously, one can appreciate the importance of discovering new ways beyond the classical one, I mean the traditional method, to find stability condition for compact objects. And we focus our study in this direction. Okay, one way to solve, there are actually two ways to solve the Einstein equation, TOV equations, from the name Tolman, Oppenheimer, and Volkoff. The first one is to use a realistic equation of states and try to find out all the configuration which correspond to this equation of states. The other way, which is very useful, is to use some analytical solution. We have a lot of analytical solutions of these equations, maybe 200, but only few of them, they have physical meaning. For example, the most known and analytical solution of the TOV equation is the Schwarzschild solution, or let's say the uniform distribution solution, where the density is uniform inside of the star. Of course, this is approximation, but it works very nicely in this object. And the second one is the Tolman solution, which also very nice solution to describe this realistic object. But in our case, we use this solution just not only to get some physical insight, but also to check the accuracy of our codes, because we perform a Fourier transform and we like to be sure that everything works nicely. Okay. Now, let's go to the application first to realistic compact opposite. We have some application, as I told before, in neutron star using hadronic equation of states. Well, we use many, I think around 20-25 equation of states. Also, in the case of quark stars, we use corresponding equation of state which correspond to quark matter and have this kind of form. This is the pressure and energy, and also there is a kind of parametrization. And finally, we have the hybrid equation of states, where, as you can see also here, in the exterior in the outer part of this star, we have hadronic matter, for example, and the interior we have quark matter, and this is the equation of states for whole the compact object. Let me present some results about firstly neutron star and quark star. What we found and that if we try to generalize the idea of Glaser, we found that there is only one case where there is agreement between the maximum mass and the minimum of configuration entropy. The black diamonds corresponds to the traditional method, where the open cycles here is the minimum of configuration entropy. You can see here, but in all these cases of realistic equation of states, there is a disagreement. Of course, there is not big difference, but there is a difference. There is no agreement between the results. There is only one case. The one case is the Fermi free gas, where also Glaser found in his paper, and there is full agreement. The minimization of configuration entropy is the same, is an agreement with the maximum mass of this neutron star. Also, this figure is similar. This is a figure diagram about mass and radius. This is about mass and central density, and also configuration entropy and the central density and the central value of the density. You can see here that there is not agreement. The same problem, the same disagreement holds also in the case of quark star. As you can see here, for example, 4 cases for 4 equations of states, there is also disagreement between the maximum mass and the configuration entropy. Also, you can see here when I plot the mass with the central density or the configurational entropy in the stellar density. This was, we didn't expect it. Actually, when we started to do all this kind of calculation, we expect that there is an agreement. And try to understand why there is a problem. Okay, just let me show you about also the Hunter star. Here there is an agreement, but this is artificial because it's the place where the phase transition takes place, and this is we expected that there is agreement between the traditional method and the CE method, but for the second maximum also there is a kind of disagreement. Okay, this was the first our finding in the first paper, and our conclusion was that there is some general rule to correlate the configurational entropy, this is an information property, with the maximum mass, which originated from some traditional method, well-known traditional method. But in our mind was that in one case, in the Fermi gas model, there is a big agreement. For us, it was very surprising, and we tried to think why there is this kind of disagreement. And only one case is we have the minimum of configurational entropy and the stability point, there is an agreement. Okay, now we extend our study in case to include fermion and boson star. This may be described dark matter star or whatever, and we consider Fermi gas, but with interaction. This is a equation of states of the Fermi gas. This is a part corresponding to the kinetic energy, and this is the interaction energy, both from the energy and pressure. Also, we have this equation of state which describes interacting boson gas. We take 3 models. There are many other models, but this is some very well-known model with many applications. And in this case, it was very surprising because we found that there is, in the most of the cases, depending a little bit on the strength of the interaction between fermion or between bosons, we found that there is almost full agreement between the maximum mass and the minimum of CE. We can see in all this figure, for example, in this figure, where I describe the mass with the radius, the mass with the central value of the density, and the configuration entropy with the central density. This is for fermions, and this is correspond to boson. In all these cases, you can see that it is a very good agreement of the results. Also, for the other equation of states for the boson gas, you can see here that the agreement is very nice, and we try to think why this happened. Why this happened? Also, I brought here just to have a better view and to extend the systematic study with the compactness. This is the configuration entropy as a function of the compactness. How compact is the object? There is a very good disagreement in most of the cases, depending, as I told before, on the strength of the interaction. But the agreement is very nice. Also, the same here. And here I present also the accuracy of the information method with the help of configuration entropy. You can see here that the agreement is very nice concerning the mass, the radius, and the compactness. A very good agreement between these two completely different methods. There is a disagreement only in the central value of the density. That is the only point. But for mass, radius, and compactness, the agreement is very nice. Also, present here some results. You can see here that the percentage is less than 10 in the most of the cases, except for central density. And the conclusion of this study and some comments. We try to correlate the configurational entropy with the stability point, as I told before. This was the starting point of this idea, is that if we found another way to predict, for example, in this compact object, we can also apply to another object, or to extend the study in another topic of physics. But let's say concerning the compact object, if we found an additional way to predict the minimum with information theory, this will be very nice and an additional method. Of course, I have to say that I have to note here that the existence of the stable configuration is a property of gravity and independent of the equation of state. In any case, independently of the equation of state, we have some kind of stable point. However, the specific location of the stability point is influenced by the underlying equation of state. That means the equation of state affects where exactly is this point. First, Glaser published a paper, and he said that, in compact object maybe works nicely this minimization of configurational entropy, and I predict the stability point. But we found that if we extend the study in neutron star, in quark star, in Hadron star, there is a disagreement. And this is a suggestion, and we think that maybe this is due to the very complex behavior of neutron star, even in quark star, in Hadron star. When the structure of this object is, let's say, complex, then it's not so easy to find agreement between this method. But in the case where the structure is not so complex, for example, in fermion stars or in boson star, in this case, we found very, very nice agreement. That means that the configuration entropy, this is one of the conclusions, the configuration entropy is a very nice method, or let's say tool or whatever, to study this object, but considering that the structure is not so complex. If we combine these recent works, this is our main conclusions. This is the main founding of our study. Of course, we would like to extend this study to another object, or to try to understand, for example, in the case of quark star, where quark star they don't have so complex, they don't have so complex structure. Why there is a disagreement? This is a point we try to find out why there is disagreement between the entropy, the minimum entropy, and the stability point. This is a general, this is, let's say, for a future study. And about the collaboration is consists of two groups. The group here in Aristotle University of Thessaloniki consists by my postdoc Moyocoyani and my PhD student Charles and Vicaris, and also Professor Panos, and the collaboration with the group of Prague, Professor Petousis and Veselski from the Institute of Experimental and Applied Physics in Prague. And also I present here the three main papers about this problem. The first one is from Glaser, which is the initial point, the idea. The idea is from Professor Glaser. And our two recent papers, we try to extend the study of Glaser into find some conclusions about this problem. Thank you for your attention.
Okay, thank you. Thank you, Professor Moustakidis. If we have questions about this very interesting talk, feel free to write them in the chats, whether in WhatsApp or the YouTube channel. And now let me introduce our next speaker. Our next speaker is Professor Fernando del Río Haza. He's working in the physics department here at the Universidad Autónoma Metropolitana Iztapalapa. His talk is entitled On Information, Entropy, and Early Stone Tools. Professor, the microphone is yours.
Well, I thank you very much to the organizers for inviting me to this. Thank you for inviting me to this. Which is the light? Yes. For inviting me to this splendid symposium, and I'm going to speak about a work that we have been developing for the last couple of years. It's still in the way of being built up. It's not finished, but we have found some interesting things. No. Hacia abajo. Okay. No. So we know there are at least three levels at which we can see entropy: at the thermodynamic level, at the entropic level, no, and also at the informational level. No. I'm going to speak about entropy associated with ecological problems, in particular with the analysis of very early Paleolithic stone tools and their manufactural process. And there has been a lot of work on applications of information theory to archaeology, mostly following the same type of work done in ecology, in the sense of characterizing things like richness of a collection, heterogeneity of a collection, and so on. But here we're going to speak something different, so it's an addition to what has happened. We already did some work in the last couple of years and was published this year on a physics journal. We are physicists. We have just started to interact with archaeologists. No? And what we did was to determine the probability that a given stone tool, or a stone that looks like a stone tool, could have been produced by natural means. That is, by by eco means, as the archaeologists would say. It's not an artifact of humans or hominins, as one's called. No. So we determined that probability. We use Shannon's information and an entropy, the divergence, the KL divergence. We studied 20 stone tools from about the earliest ones, which are 3.3 million years old, to some which are just a few hundred thousand years old. And the main result was we found that the probability, which I mentioned, is very, very low. That is, these stone tools, even the earliest one, was very improbable that they were made by natural means. No, and also that with the time of this span of time of 3 million years, the technology changed a lot, and also changed the probability of these tools, and also changed the entropy of the tools. The entropy of the tools we found out, the entropy associated with the tool, that is much less than the entropy associated to a stone that is subjected to the same number of blows, but not in an orderly way. And this entropy difference between the tool and the rough stone increases as the technology advances. This is something, both things were known to archaeologists, but as I told them when I spoke to them about this, I'm not breaking news, but I'm giving numbers to you. You knew this, but they knew it only qualitatively. They didn't have a number with it. Now we can put a number to it. No. So, but what I'm going to speak today is a physical, a statistical mechanical type of basis for this approach. I won't give you new results, just a different grounding of the same work. And on this I'm going to rely on a paper by Boltzmann in 1877, no, where he first introduced the statistical meaning of what is it? Oh, it doesn't show here, but anyhow, the statistical meaning of entropy, no? And actually he speaks about 3 levels of states. The thermodynamic state, no, the same that all the macroscopic state, the microscopic or mechanical state, and he speaks of the states that correspond to different possibilities of the thermodynamic state to be either in equilibrium or not in equilibrium, depending on the distribution of the different properties among these molecules. Specifically, he speaks about how energy can be distributed among the molecules and different distributions, and he then makes the big proposal, no, that the probability of the system being in one of these states is proportional to the number of complexions. The complexions for Boltzmann are what we later have called the microstates, no, and compatible with distributions and accessible in the thermodynamic state. That's compatible with thermodynamic state. And then, of course, he looks for the most stable states, which corresponds to equilibrium, and because the logarithm of and makes the logarithm of this probability, he makes it makes the connection to entropy. Okay. Now, what happens with a stone tool? This is an obsidian tool. Now, there are many types of stones that can be used to this. But what I would like to, I'm sorry I cannot, but I will show it here because this doesn't, I can see the pointer here. These large regions here are characteristic of the way certain type of stone break when hit in a certain way. They are called conchoidal fractures. No? Obsidian is like glass. When a piece of glass is shot by a projectile, it breaks like that. Those lines there are the traces of the shock wave that break the glass. No? And actually, all the stone tools, well, 95% of stone tools are carved this way. No? And it's the discovery of this way of breaking tools which made the possibility of really creating a technology 3 million years ago. No? So this is the main characteristic of these tools. These are very obvious. This is a stone tool from the Anthropological Museum here, no, and this is a very large one, no, and I will refer to we won't do that. I mean, the archaeologists do that. Well, then the archaeologists produce something like this drawing here on the right, you know, in which the different scars, as they are called, you know, I mark here by these regions on the right, and the arrows here are the interpretation of the archaeologists of how the shock wave moves. Okay. And so this is what the archaeologists do, this in this case it would be easy. In all the cases, not that easy. So what characterizes the stone are these scars. Well, now each scar is made by the following: is made by a blow or a stroke in a certain point of the surface. This would be a simple representation of the surface of the stone at a certain point, you know, which can be characterized by a vector. But actually, if one defines the shape of the stone, one only needs two angles to define this vector here, and also the direction of the stone. So it needs a vector r and a vector k to establish what a stroke is. A stroke is a combination of a position vector and a direction vector. And so the state of the stone can be is just as it shows there, is that by it's a configuration. This is not a phase space because there is no momentum. It is only a configuration space. A four-dimensional configuration space, because each of the two vectors has only two dimensions. There are two dimensions. So one needs only a sphere for the position and a hemisphere for the blow, because the blow has to be given from the outside, and we are assuming a convex stone. No. So one has omega is the directional space, which is 2 pi. Omega is 2 pi is the available directional space, and A is the positional space, which depends on the shape and the size of the stone. As in statistical mechanics is done, it's convenient to introduce cells, both in area delta A and in solid angle delta omega, to have a discrete description, a discrete space, no, and so the elementary configuration space is just given by a set of many cells. How many? You cell number 1, 2, 3, so whatever, no. And there is a total number of cells, which is very large. A total number of actually they are something like solid angle cones, no, which is the total solid angle available divided by the elemental stone, the elemental solid angle cone. No, this is very large. Actually, there is very little information about how delta omega, small delta omega, can be. So we have taken this. I will speak about what this is, but this is about that number is about 2,000. So there are many cells. There are not as many as in statistical mechanics, but there are thousands and hundreds of thousands of cells. No. Now, let me see. It was okay. Yes. So let's think about the following experiment. It's a Rolling Stone experiment. No? Imagine we get many stones before they are being worked, no? And we have many, and subject them to the same number of blows, all of them, in a random way, all of them, no? And at the end, no, and they receive a certain number of blows. This could be when one could think of an avalanche, or the cobbles in the bed of a river, no, that are hit when they roll, no, or even in some beaches, no, and examine each stone to determine whether the alpha stroke will say which stroke it is, whether this stroke hit or not in a certain region of area delta, capital delta A, or within a certain solid angle cone delta, capital delta omega. No, of course these are part of the configurational spaces. No, and they are supposed to form a partition of the total configuration space, and we ask that. No, so we can. No, well, there it is. No. So at the beginning, I mean, to characterize a stone tool, this is the same example I showed you with the arrows, but now we are marking there those red squares, red rectangles there, which signal the points of the regions where the stone had to be struck in order to produce a similar, well, that particular tool or a similar tool, because I mean, the tools are not perfect. The stroke or the blow could be given a few millimeters to one side or to the another and still work effectively as a tool. That's what we call this an effective configuration, which is not on an elemental cell, a small elemental cell, as we said. The elemental cell, the size is defined by the precision which fits with the instrument, and or in the case of the stone tool, the instrument and the artisan was able to hit it, no, or the process of the avalanche or whatever. No, but here it has to do with the possible use of the capital deltas A and delta omega have to do with the possible perturbation of the elemental cells, both in area or in solid angle, that keep the effective use of the tool. And these blows have two characteristics. One characteristic is that these areas are localized, no, and there. The other is that is, if we let the rectangles grow too much, no, there won't be a tool. No, it will happen as here. Here well, I'm just writing. I'm just drawing on the right. Have the area to be hit by the stone, by the blow. It won't give an indefinite pattern. No, so if it's going to be an ordered pattern, they have to be small, and they have to be correlated. On the first level, let's say, of this theory, we are going to show that it's enough for the blows to be localized in order to produce effect. And we're working on now with correlated strokes, but I won't have time to go through that. So we're going to distinguish between the localized strokes on the left and the and the situation on the right, which will will consist of non-localized strokes, because here if I only know that the strokes is in one half of the area, well, the strokes will be completely scattered. So for some reason I cannot find this. No? So the effective configuration is again it's a configuration, but now with the capital deltas, no? And if the capital deltas are smaller than the available configurations, one has the focus blows and the scatter blows correspond to the picture on the right, on the last slide, correspond to the scatter configuration. But the fraction of stones corresponding to this case, in this case, in the experiment, determines the probability, of course, assuming that one has a number sufficiently large of stones thrown in the experiment. So that's the probability of that, and for a configuration, which is a set of those probabilities, will give the probability of the configuration. It's all very simple. Okay. Now, what are our basis assumptions? I'm going to speak. We're going to see the simplest part of the simplest level of the theory. Strokes hit randomly on the surface of the stone. If the strokes are random, K and R are independent events. There is no correlation between the point where the stroke hits and its direction. No, so one speaks of each of them by itself. For a continuous configuration space, no, the probability density P of U and B are the two polar angles, that they define the point on the surface of the sphere where the blow was made. No? So the probability on delta A, no, is just the integral of P, but again, because of the same randomness, no, one can show, and this problem of stones being hit by other stones or by the floor or by something else, you know, has been worked by geologists who worry about why stones in some beaches have very peculiar shapes, you know? And Domokos is one of the last ones, and he shows this was based on work that was initiated by Fiery several decades ago, and they show that the probability of hitting in one point of the surface is a function of the curvatures of the mean curvature and of the Gaussian curvature. Actually, when using their work, we could find out what this probability is in terms of these curvatures and in terms of the effective radius of the stone, which is the capital Rn. So P of UV is that equation downstairs. Well, down of on the slide. No, and we are using that to calculate the effect of curvature. What we are going to make the spherical cow approximation, no, and suppose that the stone is spherical, no. So I mean we have results for that, but they are too complicated. Well, a little complicated. So we're going to use the spherical model, no, the spherical model in which well, the probability for joint possible outcomes to hit in these regions, no, well, first they can they factorize because they are independent, and being random and being a sphere, no, there are uniform and being normalized. They are these densities, and integrating them, one gets that probability to hit delta A and delta omega over the total area and solid angle availables. No, and but in terms of the elemental cells, just multiplying and divided by the small deltas, no, one finds out that capital delta A over A yields the number of elemental cells with respect to the total number of cells, and this is the total number of solid angle cells over the total number of cells, so that okay, so the probability, which is that there, well, at the end, no, the probability of the effective configuration use the product, which is just the product of all the probabilities for each block because they are independent, and since the probability for each blow to be positive, that is for the event of blowing having actually hit on the area and the solid angle is the relative number of cells, of elemental cells, no, which is that the probability of observed stone on that effective cell equals the fraction of accessible elemental cells. This is exactly the same conclusion that Boltzmann finds, no, that the probability to observe a thermodynamic state is equals the fraction of microscopic states, of microstates. No? So now let's go back to the. Okay. Now let's see one stroke as an event. A stroke has 4 possible outcomes, both positive in area and solid angle, or one positive and one negative, no, which are there. In the example of that stone that I put, which is a stone from a place in Ethiopia, and about a 1.5 million, about 2.5 million years old, no, this probability becomes that, no, the 4 probabilities is the full probability, the 2 positive probabilities, the probability of hitting the stone in those places, no, is 10 to the, well, something 10 to the minus 5. The probability of hitting one or the other is about 1,000, and the probability of not hitting anything, that is the probability for the rough state, is almost 1. No, as shown in the graph. No, as we define the scattered state, always the probability of the scattered state is always, or scatter blow is always 1/4, 1/4, 1/4, and it's uniform, of course, no? And which got some interesting things, no? Now, the probability of the tool, which is just the product of for the focalized strokes, no? Over all the M, we're supposing that there are M strokes, no, in our case, and for that tool, the probability becomes 10 to the minus 41, which is a very small number, no? For the rough stone, it's always to hit both positive on one side of the stone is 10 to the minus 6, which is also small because there are 9 of them in this case, no? And following Shannon or UAM, we can look also at the information associated to this probability of the tool in both cases. No, at the sum of those logarithms. Now we are using here the natural logarithms because we are, well, I'm a physicist now. I will change to base 2 logarithms at some point. No, but the information contained in the tool of the example is 135 nats. No, and for the rough stone is only 12. So it's a factor of about 10 more information on the tool than on the rough stone. No, well, this is for some people who have no idea of what, who have not been able to look at the entropy of an event with only 2 possibilities. No, in this case, the entropy of the tool corresponds to what is written at the bottom, not just the sum of the entropies of all the blows, both focalized and roughs. No, and in our example, the entropy of the tool is about 6,000. No, and the entropy of the stone rough is 18. No, so the scatter process leads to about 3,000 more, an entropy of 3,000 larger than the other one. No, so it's well. No, I want to refer to the Kullback-Leiber divergence. No. So some results. Well, how we select the parameters, the elemental parameters, the small delta A and omega. No? Well, there is some information by the archaeologists, not many. No, I refer to some here. No, our choice of parameters is at the bottom. No, delta A is about 1/3 of a square centimeter. No, and delta omega is about 1,000 of pi steroradians. No, this is an angle of about 3.5, an epic angle of about 3.5 degrees. The moon distends an angle of about 0.5 steroradians. I mean 0.5 degrees, the apex. Now, so it's a small angle. Actually, I think that we, given the results, probably we exaggerated the. Now, which stone tools we analyze? The oldest one is that one, no? We have 10 different archaeological sites and two artifacts or 2 stones from each site. Also a total of 20. The oldest one is from Lomeke, Kenya, which is the oldest tool that has been found. No. And has only, I'm writing that these are two stones, two tools. The one on the right, or I mean the one on the left, has M stroke, 4 strokes, and the one on the right has only 9 strokes. No. And then there is another from, this was in Kenya, in West Turkana, close to the Turkana Lake. In another place in Ethiopia, about 1 million years closer, there are these two. The one on the left is the one I took as an example. It has 9 blows. The one on the right has 10 blows. It's also in Ethiopia. For some reason, I think, okay. No, I missed one. Okay. Okay. There is another from Ethiopia also, a little earlier. No? This is a small tool, but which has 4 and 20. This one on the right is up on both sides, on both faces. It's a bifacial, it's called. No, these ones on below are much say about 1 million years old. There are 2, but since they are bifacial, the 2 sides are shown for each. No, the one on the left. These are called bifacial stone tools. The one on the left has 41 blows. The one on the right has 35 blows. And as you see, as I told you, the archaeologists either draw on drawings or on the photographs, point out to where the blows, how the blows were stricken. No. And the earliest one, which is about where the Neanderthal were around, no, there are 2. This is from a place in France, no, and one has 19 blows and the other has 37 blows. The one on the right. Now, the probability of stone tools. Compare the probabilities of stone tools versus the rough stones. No, the earliest one, the Lomeki one, the probability of the tool was 10 to the minus 21, and the probability of the rough stone was 10 to the minus 3. I have to say something here. Here we're looking at the probability of creating a single particular tool, and a singular particular artifact. But there are many others that could be equated, that can say. They are very similar ones, no? Which is the same as the number of how many ways can I choose. Let's say in the Lomeki one that there are 4 blows. How many ways can I choose 4 blows out of the whole full of possible regions? No? Because this could be in some side, when another side, when another side. So it's a combinatorial factor, which is very simple. It's very largely combinatorial factor. Actually, it grows not as fast as the number of possibilities, but it reduces the probability. And for instance, this probability of this tool is reduced to about, to be of the same size of this, to about 10 to the minus 3. No, because there are, let's say, 10 to the 18 ways of choosing that tool. No, that is what happens then. In this case, is that the probability of this tool is only about 1 in what's about 1 in 10,000, not 10 to the minus 4, no? Which means that it's not that if I look at 10 to the 4 stones, 10,000 stones, I will find one which will look like that. And that has made, that explains why many people are skeptical that thing is a tool. You can say it's too little to be true. But for these ones, no, the number of combinations which I haven't shown here, no. For instance, for these, the most complicated one are these from Elka Conturi and this one, which have the smaller probability. But this one is reduced to about -9 to the 40, and this to about -9 to the 35. No, they're still very, very small. No, so even taking into account the multiplicity of possible different equivalent tools, no, the probability of finding any one of them is very small. But the rough ones are not that small. The relative probabilities. How's the entropy? This entropy was calculated in the original paper, so this was a la Shannon with the base 2 logarithms. No? So on the top left panel, one has the entropy. The entropy of the tool is the green bottom line, which the entropy is very small. No, it's of the order of less than 10. No, but the entropy of the rough stone is very large. The relative entropy is here. No, I mean it's just the division of the other two. In all cases, the entropy of the tool is much smaller than the one of the. There is a very sharp decrease on the relative entropy for the last four sites, for the last 4 items, no, and one could say that that's because the stones, the rough stones, its entropy grows very much. What happens is that because entropy being additive, the more blows they are, the entropy grows. No? So what is interesting then is that this decrease is not only because the entropy of the rough stone grows, but as we can see on the left hand side on the green line, for the last few points, there is also a decrease. No? This one here is the amount of information, but something happened to this is the amount of information. No, of course, I mean this is the reverse of the entropy in a way. No, there is a lot of information on the tool and very little information on the rough stone, and the amount of information divided by the number of blows, that is by so. No, this is always 4 for the rough stones, because there are only 4 possibilities: or above or below, or in or outside half the hemisphere. No, so it's always like that. But for the others, the amount of information decreases, but then they increase again more or less at the same time. This, if the sample were better, no, this would imply a change in technology. No, at this time, the archaeologically, our sample is very small. No, so I don't want to stress the archaeological consequences of this. No. Well, there is there. So this is the KL divergence. Again, I mean, taken as reference the rough stone. Again, I mean, there is a much larger amount of information in the tool. Now, conclusions. Well, the first is that the entropy of a lithic tool cannot only be defined a la Shannon, but also a la Boltzmann, so to say. So this fact establishes a bridge between the two types of looking at the stone tools, no, by information theory or statistically, by statistical mechanics, no. Now again, now the probability, of course, I mean the results are the same. The probability that the stone tool is produced naturally is very, very, very small, much less than observing the same type of thing on a rough stone. Now, the entropy associated with stone is much smaller than that of the roughly natural stone, which is the maximum entropy for this type of process as occurs to a thermodynamic system when reaching equilibrium. I mean, it was a uniform distribution, no, which corresponds to the maximum entropy. No? So that the fact that the entropy decreases with the advance of technology would mean going further away from equilibrium in this sense. And the lithic tool has the lithic proof and its process of manufacture contains an enormous amount of information. What I pointed out about the results, analysis of these 20 stones shows that the entropy decreases with time, the amount of information increases. No, but as I said, the sample is too small to draw archaeological conclusions. No? Well, for the thanks. Now, we have incorporated already an ellipsoidal model, and it doesn't change qualitatively the results. No? We have not only for all the pieces, only for a few of them. That's why I don't show it anything. No? No? Now, the localized configuration stroke is being extended to account for correlation between strokes, because in this sense, I mean, the problem of having assumed a spherical stone is saying this is improved by taking an ellipsoidal, for instance, or something more realistic, most closer to the real shape of stone. But the correlation of the ordering of the ray, it has to be taken into account also. No? And from what we have seen in very simple examples, it decreases the probability even more, so it will have a stronger effect. No? Now these parameters, I mean, which we chose from the available information, we can optimize their determination by Bayesian analysis, that is assuming some distribution of values for both, no, from the archaeological information, no. But for the project itself, most importantly, no, we have already aroused the interest of many archaeologists, and some of them are willing to collaborate with us, so we can dress this up. Okay? Well, and thank you very much.
Well, let's thank Professor Fernando del Río for this very interesting talk, and we invite the participants to write down their questions in the chats, again, whether on WhatsApp or on the YouTube channel. We're now going to have a break for the lunch, and we will be back at 4 p.m. Mexico City time. Thank you all.